distinct possible MXN structures. So what basically these materials are? Those are layers of transition metals bonded by carbons, nitrogen, or their mix. Distinct. And there can be, of course, at least one basically these materials, two layers of transition metal, that can be three layers of transition metals bonded by carbons, nitrogen, or from their mix. Distinct. And there can be, of course, at least one basically these materials, two layers of transition metals, developing them three in layers of transition metals bonded by carbons, nitrogen, or from their mix. Distinct. And there can be, of course, at least one basically these materials, two layers of transition metals, developing them three in layers of transition metals bonded by carbon.
하나, 둘, 셋, 넷, 원, 투, 쓰리, 포. 마이크 테스트, 마이크 테스트. 하나, 둘, 셋, 넷, 원, 투, 쓰리, 포. 마이크 테스트, 마이크 테스트. 하나, 둘, 셋, 넷, 원, 투, 쓰리, 포. 마이크 테스트, 마이크 테스트. 하나, 둘, 셋, 넷, 원, 투, 쓰리, 포. 마이크 테스트, 마이크 테스트. 하나, 둘, 셋, 넷, 원, 투, 쓰리, 포. 마이크 테스트, 마이크 테스트. 하나, 둘, 셋, 넷, 원, 투, 쓰리, 포. 마이크 테스트, 마이크 테스트. 하나, 둘, 셋, 넷, 원, 투, 쓰리, 포. 마이크 테스트, 마이크 테스트. 하나, 둘, 셋, 넷, 원, 투, 쓰리, 포. 마이크 테스트, 마이크 테스트. 하나, 둘, 셋, 넷, 원, 투, 쓰리, 포. 마이크 테스트, 마이크 테스트. 둘, 셋, 넷, 원, 투, 쓰리, 포. 마이크 테스트, 마이크 테스트. net 1, 2, 3, 4. 마이크 테스트, 마이크 테스트. 둘, 셋, 넷, 1, 2, 3, 4. 마이크 테스트, 마이크 테스트. 둘, 셋, 넷, 1, 2, 3, 4.
But due to COVID-19, our conference was postponed from last August to the February. We was thinking like the situation will get better, but unfortunately, again, the situation is same. So due to that reason, our international due to COVID-19 speakers, plenary speakers, but unfortunately, this year, almost all of our international speakers, plenary, keynote, and invited speakers, they are not able.
I wish you all productive 3 days of the conference, many interesting talks, online discussions, and of course, we all can be connected via email. But let me switch to the topic of my presentation. I am going to spend next 40 minutes or so speaking about two-dimensional materials. A very large family of 2D materials, which we call MXenes. But before MXenes, definitely there have been other materials. Graphene is certainly the first one. You don't need to be expert in carbon materials, 2D nanomaterials to know at least something about graphene. Discovery of exciting physics in graphene by Andrew Geim, Kostya Novoselov in 2004 led to increasing interest to many other two-dimensional materials which are available. Some of them have been known for a very long time: hexagonal boron nitride, clay, 2D oxides, 2D chalcogenides, which were actually separated into single layers even before graphene. But a number of them were discovered later, produced from materials often which don't have two-dimensional, not two-dimensional, layered van der Waals bonded or weakly bonded precursors, like silicene, germanine, borophene, phosphorine. So people really got excited about opportunities in the two-dimensional world. And the reason for this is because 2D materials show a very wide variety of electronic properties. And they range from semiconductors to insulators to semi-metals. Graphene, for example, a zero bandgap semiconductor. MXenes, you will hear about today, actually add a large family of 2D metals to this family. The atomically thin, any thin material is flexible. And if it's additional strong mechanically, it can truly be made into flexible and also transparent structures. You can see through several atoms, even if this is a heavy metal like gold. And also, of course, high surface area of 2D materials open opportunities for application, gas separation, to catalysis, to adsorption, to surface redox processes. And in 2011, working with my colleague, Professor Michel Barzoum, and our PhD students, Michel Naguib, and several other students, postdocs in my group, we found that transition metal carbides and nitrides, in particular titanium 332 was the first one discovered, can also form two-dimensional structures, the ones which have not been known to exist, not predicted to exist before. And these materials are already shaping into a very, very large family. So what are MXenes? M stands for a transition metal. One of these elements in blue. X stands for carbon or nitrogen. And TX at the end stands for surface termination. It can be oxygen, fluorine, chlorine, actually chalcogens, other halogens. It can be OH, which actually increases by an order of magnitude of the number of distinct possible MXene structures. So what basically these materials are? Those are layers of transition metals bonded by carbons, nitrogen, or their mix. And there can be, of course, at least one carbon nitrogen, 2 layers of transition metal, but can be 3, 4 layers of transition metals. And initially, we made them from materials which is known max phases. Michel Barzoum is really the father of that field, developing them into materials. They were discovered by Novotny and others before that here, but he really studied them to make ceramics, making high temperature materials. If you look at the max phases, they are basically layers of carbides or nitrides connected by monatomic layers of one of these blue elements. In particular, aluminum, silicon, gallium are the ones that have been etched away. We use the same method as we have been using for many years to make, for example, carbide-derived carbons, removing monatomic layers of this element over microns distances to release two-dimensional sheets of carbides or nitrides here. And as a result, we get materials with this variety of structures like M2C, M3C2, M4C3. Moreover, we also can have mix of carbon and nitrogen or potentially different transition metals here. What is important in synthesis of these materials? Unlike, say, graphene or boron nitride, they cannot be easily produced by mechanical exfoliation or shearing because there are strong metallic covalent or ionic bonds between this A element, for example, aluminum, silicon, sulfur, and the transition metal. So you have to etch it here. But when you etch it and remove the connecting layers, we replace strong bonds with weak van der Waals or hydrogen bonds between the terminated layers. Naturally, during the chemical reaction, transition metal don't stay unaffected. So they will grab, for example, if etching is done in aqueous environments, oxygen, OH, or fluorine, chlorine, whatever is the etchant. We use initially HF solution. There are many different recipes now, including electrochemical, hydrothermal etching. Also, emulsion salts can be used. In this case, you usually end up with halogen on the surface, like, for example, chlorine here. But the result is the same. The bonding, strong chemical bonding, is replaced by weak bonding. When you intercalate organic molecules or ions, it's possible, just exactly like in many other 2D materials, weakly bonded 2D materials, delaminate them into single layers. What is wonderful about MXenes? This is a very, very large family of materials. You may remember how many M elements I showed you. There is a dozen of elements there. And also carbon and nitrogen. And you can form simple structures with 2, 3, 4 layers of metal and 1, 2, or 3 layers of carbon nitrogen. But you can make solid solution, an actually infinite number. You can mix carbon and nitrogen in the carbide nitride sublattice, but you can also mix transition metals, and many of them form solid solution with infinite solubility. But moreover, it's possible to make with some elements atomic sandwiches when one element is on the surface, for example, moly, another is in the middle, for example, titanium. And it's possible to go even further, pushing atomistic design to the level where it's possible to make alternating metal atomic columns, and even further, you can etch one of them, making materials which have like a missing rows of atoms ordered divergency maxine. So those are in plane ordered, those are out of plane ordered. So we end up with more than 100 of stoichiometric structures. If you consider surface termination, this will be more than 1,000 of stoichiometric distinct structures. But with solid solution, the number is really infinite. Moreover, discoveries continue. Just like a year ago, it was published in January issue of ACS Nano, we showed that it's possible to make materials with 5 layers of transition metal, 4 layers of carbon, moly 4 VC4. And actually, there are quite a few materials like dichalcogenides with 3 layers of transition of elements. Oxides, others, they're usually thin. Go into distinct structures with 10 or more layers of atoms and all sheets are exactly the same is also truly unique for MXenes. So these materials have many interesting features, but what is also very important, the family keeps growing. Just in 2020, this new structure, or basically entire subfamily of materials, was added to MXenes. Michel Barzoum's group showed the possibility of etching of MXene using HF in organic solutions. General Lewis acidic etching from molten salt has been demonstrated by Qin Huang from Nimte, from Ningbo. And this material showed very interesting electrochemical properties. And Dmitry Talapin from University of Chicago explored similar synthesis to show a very large variety of surface termination, unique, clean, pure surface terminations, and produce the first superconducting MXene. And the growth goes on and on. So basically, we have very large already, more than 30 stoichiometric compositions have been demonstrated. Couple of dozens of solid solutions have been published. And potentially, there is no limit to how many structures and composition you can create in this system. However, are they good for anything? Why would anyone bother to add more two-dimensional materials to the ones we have? There is a good reason for this. As I already mentioned, majority of 2D materials are poor conductors. Even graphene, which is praised, we know it's strongly dependent on stoichiometry.
Eutectics with tin that have their melting point below room temperature. Now, in our work, we discovered somewhat serendipitously, or one might say by accident, because we were using gallium for some other research, that we could mix, for example, graphene oxide into liquid gallium and make these putty-like composites. We refer to this as gallium putty, or use this acronym here. So as I mentioned, our initial experiments were with graphene oxide, and we found by mixing by hand and then using various mechanical stirring devices that we could load up to about 1.8%, and above that loading level, the composite material would become too viscous to mix further in, further amounts of graphene oxide in. Now, if we used a ball mill, we could actually get up to about 8.08%. So I'll show this, well, I hope to show a video here, but it's not showing. In any case, what the video would have shown is that we could roll this around in our hand, something like putty. Ah, here it is. We could cast this into any shape. So Chunhui Wang worked on making these putty-like materials and showing that they could be formed into various sorts of figures and into thin films and rods and so on. A very interesting thing is that when the material would solidify, it didn't really show the standard volume expansion that gallium has. Gallium is like water in that it has that unusual phase diagram in which the solid is actually less dense than the liquid, but the change in density of gallium when it solidifies can be problematic for certain applications. It's also, of course, scientifically interesting that we see this difference. Another thing is that gallium, as many of you are aware, like mercury and indium, amalgamates with almost all the metals, including at room temperature. Tungsten typically has to be heated a bit. But in our putty-like form, we can contact these metals and also many other surfaces and not have the gallium actually mixing with the substrate. And this is valuable for certain applications. So in the cross-section images that you're looking at here, where we created a cross-section and looked with scanning electron microscopy, we could actually find evidence of the dispersed graphene oxide platelets. Some are multi-layer, dispersed throughout the gallium. If we heat treated our putty-like mixture, we could end up with a gallium with reduced graphene oxide because of driving off the oxygen from the graphene oxide sheets. And we'd end up with that material allowing us to reform the putty. And then that putty would have a conductive platelet inside it. We could not, however, at least in this work, directly take reduced graphene oxide and mix it into gallium. So we took this somewhat circuitous route to first make this foam-like material, which involved evolution of carbon monoxide and carbon dioxide. And then we could reform the putty-like material and eliminate these voids. I wanted to mention a couple of applications that do look promising. We studied the electromagnetic interference shielding. We found that the shielding efficiency is very, very high for the RGO film. That is to say, the gallium putty with RGO filler, which is designated in this way here. And we could put that onto paper. We could put it onto RGO film. The coating itself could be studied if on a paper that has no EMI performance itself. And basic story is that for relatively thin films, we could get a very strong shielding effectiveness. It then occurred to us to try mixing in some other types of particles after our success with graphene oxide. And I had thought that mixing in diamond might be promising for making thermal interface materials. Often I'm wrong. In this case, it happened to work rather well. We could also mix in graphite particles and silicon carbide particles. And during the course of our studies, I won't have time to go into great detail, we learned that particle size and roughness influenced whether we could make the putty-like material or not. Now, there's a fairly extensive set of literature by, for example, these workers here, but others as well, showing that a thin skin of Ga2O3, gallium oxide, will form on gallium when contacting air. And so we did control experiments where we attempted to make our putty-like material in a glove box, and we were not successful. So that was one of the indications that oxygen, which we had suspected was very important, and that it is this gallium oxide skin through constantly mixing air during the mixing of the particles that is playing perhaps a critical role in allowing the particles to be mixed into the gallium. So the sort of cartoon picture is that if this gallium oxide skin can coat the particles either entirely or to some degree, we might be able to mix into
3D, not 2D. For layered structure, the interaction between different layers are very, very weak, the one virus force. At that time, we didn't study any properties and applications of the 2H gold because the yield of the 2H gold is quite low. So fortunately, in 2015, we got the 4H gold. This gold is very, very unique. It's very, very long, and also the thickness is several nanometer, and the cross phase is different from the 2H, different from thermodynamic stable FCC phase. Based on high resolution TM imaging and other technique measurements, we use this model to demonstrate the crisis structure. It is a ABCB stacking. We call this a 4H structure. This is also one kind of hexagon structure, but different from the 2H and FCC. The important thing is here we can decide the 4H gold nanoribbon very, very pure. So we can use it for various application and property study. So normally, as a chemist or material scientist, if you can directly synthesize nanostructures with unconventional phase, that's great. Right? You can scale up, but sometimes because the unconventional phase has high energy compared to thermodynamic stable phase, it's not quite stable. So in that case, it's quite difficult to synthesize directly. However, we already have the 2H gold, 4H gold based on epitaxial growth of nanostructure. You can synthesize other 2H or 4H metals by using the 2H and 4H gold as template. So I give you some example. So here, by using the 4H gold nanoribbon as a template, you can epitaxial grow the silver on the surface. However, it's very difficult to distinguish silver and gold because they are just like twins, right? Okay, so it's very difficult to distinguish them. But however, by using element mapping, it's easy to see the gold there and also very thin layer of the silver coated on the gold. So in this part, we already have the 4H gold. So at the end, in the edge, okay, of this nanoribbon, of course, silver is 4H. Because gold and silver, just like twins, and the lattice structure is similar, lattice mismatch is very, very small. It's easy for silver to epitaxial growth on the gold. So if you change it to other element, for example, the PD, one kind of metals, so you can see, you can grow, of course, you can grow 4H PD, but structure is quite different. It's just like the island structure. We can also grow PT to get the unconventional phase, 4H phase, or even iridium and others, for example, rhodium, osmium, and ruthenium. So we can get the 4H phase of all noble metal nanostructures. But how about the other transition metal with 4H phase? Can we get it? Fortunately, we also got this kind of the 4H phase for copper, because copper is quite common for catalyst for CO2 reduction. But until now, people studied the copper-based CO2 reduction only focus on the morphology control, architecture control, and others. Nobody studied the cross phase dependent CO2 reduction on copper catalyst. This is our goal. Later, I will show some example for you. Not only single element can be epitaxial growth on the surface of the 4H gold to form the 4H on conventional phase. How about alloy? So based on our previous result, we can coat the silver on the surface to get the 4H silver. After that, if you use the galvanic reaction, you can get the PD silver, PT silver, PD silver, the alloy with a 4H gold. So for example, here, the PD silver, PT silver, 4H part is here, and also this PD silver 4H FCC structure shows better catalytic compared to the PD black. PD black is FCC structure, right? So it means 4H structure might have applications for the HER compared to normal PD black. It shows better performance, right? These are 3 elements with a 4H structure, okay? So how about the other materials, for example, magnetic materials, cobalt or nickel? Can we get the unconventional phase? So recently, we published a paper and demonstrate the growth of the cobalt on the surface of a 4H gold. So here we call this a quasi-epitaxial growth. I will show it later. So here shows you some high uniform nanobranchial structure of the cobalt growth on this 4H gold. They form the core structure, right? So based on high resolution TEM image, we can see they followed this kind of the epitaxial growth, but not completely. So we call this quasi-epitaxial growth because based on the structure, okay, we can see the 6 lengths of the gold is similar to the 8 lengths of the cobalt atoms. So in that case, if you want to epitaxial growth, you have the inset part here, okay? So we can use this model to see it more clearly. So here, the 6 gold will be linked to the 6 cobalt, but after that, 1 cobalt layer will be inset here to match the length equal. Based on high resolution TEM image and also model, we found the repeated unit of the cobalt is not 7 cobalt, actually it's 14 cobalt. So this highest, the largest the cobalt unit, we call the 14H. Yeah.
On silicon carbide. So that was the graphene. But we were not so fully aware what this was good for and so on. But as a grower, we were very interested in that. And then we continued the studies and had a diploma thesis in 2008 and so on. And then 2010, it was demonstrated a very nice result of using this material. So together with other researchers, they presented a quantum resistance standard or results towards a quantum resistance standard using epitaxial graphene. And some important things which are in this context, because it's very tricky to intentionally produce 1 layer of carbon on the surface. So here you have the vapor pressures. They depend on the temperature. What are the vapor pressures? So that has an influence on the silicon to carbon ratio, how much to have this shift and so on with temperature. And in many materials, you have the steps which are formed, and they can form step bunching, which is not good for the growth. But this is also a way actually to make the graphene on silicon carbide, because you have the bilayers and then the graphene start from the edge and so on. So then the steps are very important. And in the case of silicon carbide, depending on the polytype, you have various bilayers, and then there are several small steps which are merging on that. And the surfaces can look like very different depending on how we have pre-treated the substrate before. So either there are intentionally made steps, or there will be some domains and so on, and different features. In some cases, these are not good for some some applications, but sometimes actually these features are useful. For example, on the left side, you have straight steps, and when we have such surface from the beginning, then we can create ribbons of graphene along the steps. So they don't form two-dimensional layers over the whole surface, they are ribbons, and so on. So from a research point of view, this is very exciting. And in silicon carbide, when you do silicon and carbon atom, you can stack them in different ways. You have the hexagonal ones, the 6H silicon carbide, the 4H silicon carbide, but also the cubic silicon carbide, which is very difficult to grow because it's metastable. But they have some different stacking sequences and some difference in properties. So when actually doing graphene on these surfaces, the behavior are different. If we use similar conditions, there will be different behaviors. And sometimes we need to modify the process for certain polytype and so on. But there are some very interesting features happening just due to the nature of the different polytypes. And this we did in the research. So the leading professor in the graphene in our group, Professor Ruzica Yakimova, and we had many collaborations and more collaborations. And then actually, when we made samples for free for the research, then it became so much interest that we did not know what to do with this. So then we actually started the company. So this became the second inspiration for creating utilization from the research findings. So we were able to sell material, but there is no application.
Materials that, because they are so thin, the short channel effects are reduced in these devices. So they are suitable for scaling down devices and realizing nanoscale devices. Also, photodetectors made of these 2D TMDCs show extremely high photoresponsivity and quantum efficiencies. This is because of the photogating effects from defect, ambient defect, which are quite dominant for the 2D materials. Besides electronics and optoelectronic devices, 2D TMDCs are also widely studied as an electrode materials in batteries and catalysts. One unique thing about 2D materials is that they're ideally dangling bond-free, meaning that they can be easily attached by weak van der Waals forces and create clean and atomically sharp interface in 2D heterostructures. As you can see in the Lego image, van der Waals materials can be easily attached or detached using transfer and alignment processes. So using various van der Waals materials and using their fundamental band gaps and transport properties, one can design various heterojunctions and devices with varying device performances. Also, recently, as you can see in the bottom image, right image here, 2D materials can stack with different stacking angles to show that at a certain stacking angle, interesting properties such as superconductivity or unique interlayer or hybridized extons can be found. These 2D materials are highly suitable for future flexible devices because, firstly, they have good field effect mobilities.
Good morning and welcome everyone who attend the Tuesday morning session. I'm Sang Park and I'll be the chair of this session. The topic of this session is advances in multifunctional composite materials. We have 8 speakers in this session and each speaker has 50 minutes to present their research including Q&A. The first speaker is Ji Su. She is from Tokyo Institute of Technology, and she will be presenting fluid structure interaction simulation of thermal stripping in a T-junction pipe made of functionally graded material. Ji, are you ready?
Yes.
Yes, you may share your presentation.
So thank you very much for your introduction, and it's my honor to present at AFM 2021. So now I will share my recent work with you. Good morning, professors. My name is Li Su, and I'm studying at Tokyo Institute of Technology in Japan as a doctoral student. Today, I'd like to talk to you about the fluid structure interaction simulation of thermal striping in a T-junction pipe made of functionally graded material. First is the background of functionally graded material. The concept of functionally graded material was first proposed as a thermal barrier on spaceplane in 1987. The difference between FGM and traditional composite material is shown in this picture. In traditional composite material between material A and material B, there is a specific bonding interface. While in FGM, due to the composition of change as designed gradient, there is no specific bonding interface. Therefore, the most common problem in composite material delamination would be avoided in FGM. And without the sudden phase change in material, the stress concentration would also decrease. And here is the picture shows the contents to gradient. It could be the material composition, the element dimension, the arrangement, and orientation, and so on. One of the potential applications of FGM in the industry is used in the T-junction part of pipe. At the T-junction, the turbulence caused by the mixing of hot and cold fluid has attracted many researchers' attention. Because the temperature fluctuation in the mixing part may lead to the high circle thermal fatigue in the pipe. And there are 3 kinds of flow types at the T-junction. Depending on the momentum ratio, flow at the T-junction can be classified as the stratified flow, deflecting flow, and impiping flow. According to the research conducted by JAEA, the stratified flow case will have largest temperature fluctuation, which may affect pipe most. And here is a picture showing the pipe failed due to the thermal fatigue. The temperature difference in this pipe is only 60 degrees C. So this work aims to evaluating the performance of FGM when applied to the T-junction pipe through one-way fluid structure interaction simulation. In order to complete the one-way fluid structure interaction simulation, first, the conjugate heat transfer between fluid and pipe should be done. Simulation work in this study was conducted on the axis fluid. Here is the schematic of simulated T-junction pipe. The flow in the main pipe has a 48 degrees C temperature and 1.46 meter per second velocity, while the flow in the branch pipe has lower temperature, 33 degrees C and 1 meter per second velocity. By calculating the momentum ratio, the simulated flow is a stratified flow. The flow and pipe parameters are same with the waterlock experiment conducted by JAEA. For simulating the FGM in the numerical software, the layered model was used, and 3 models are used in this study. The one-layer structural steel pipe, which can be treated as the homogeneous material pipe, And the two layer is the traditional composite material, and N layer is the FGM pipe. The graded two material is structured steel and low thermal conductivity ceramic. In the 8-layer model, the material property is calculated from the power law distribution of FGM, and this power law index in the 8-layer model is 1. So before going to the T-junction pipe simulation, the performance of using layer model to simulate FGM is changed. A transient heat conduction problem in FGM pipe was conducted. As shown in this picture, the pipe has graded thermal conductivity and specific heat. By comparing the temperature distribution and the temperature history between analytical result and simulation result on the layered model, and we can find the 8-layer and 16-layer models could represent the FGM well and match with the analytical solution. This shows the feasibility of using layered model to simulate FGM in numerical software. So back to the T-junction case. After the validation and verification of mesh setting, the final decided mesh information is here. The first layer of fluid at the boundary has a thickness of 1.2 times 10 minus 5 meter, which ensures the Y plus value during the calculation is smaller than 1. And this is the requirement for the SST K omega turbulent mode. The average length of the mesh is 4 millimeter. And with the time step 2 times 10 minus 4 seconds, the maximum current number is 0.82. It also satisfies the CFL condition. And both fluid and pipe mesh has nearly 1 million nodes. The turbulent model used in this simulation is DES SSTK omega model, which is suitable to the wall-bounded flows. And the bounded second-order implicit algorithm is used for the transient formulation as required by the DES model. The discretization method on the turbulent term is first-order upwind, while the other term is second-order or second-order upwind. The time step is fixed as 2 times 10 minus 4 seconds, and the total 7 seconds is calculated. The velocity in the boundary condition is mapped with the developed flow velocity component, and when compared with the experiment data, they give no difference. And here are the temperature counters at the end of the simulation. The temperature on the two cross sections x equal to 0.5D and 1D are used for the calculation for the root mean square number of temperature for comparing with the experimental result. It should be noticed only the data between 2 to 7 seconds was used for the statistical analysis, because the first 2 seconds it is the transition from the steady result to the transient result. By comparing the temperature fluctuation on the central line and the temperature fluctuation near the wall, we can say the present heat model reproduces the thermal striving phenomenon at the T-junction part accurately. Both the experiment and the numerical calculation show the 30° near the wall has largest fluctuation. Then, with the temperature history in the pipe, by transferring the body temperature to the transient structural module, the stress fluctuation in the pipe due to the thermal striving could be obtained. So with the temperature data from simulation result, the spectral analysis of temperature field was conducted. As shown in this picture, first the fast Fourier transfer and the power spectral density of these 3 points in the fluid domain were calculated. The sampling frequency is 100 Hz. And from the Fourier transfer result, we can find the major vibration frequency is under 13 Hz, and the 6 Hz component has the largest amplitude from each position. And in the PSD graph, we can find the temperature fluctuation in the 1D cross section. In the 1D cross section is larger than those 0.5D cross section, and the 30° direction has the largest vibration power. which is the same with the former result from RMS calculation. And the spectral analysis also conducted to those points in the pipe domain. And due to we already know the 1D surface and 30-degree direction has largest fluctuation power, the temperature, power, spectral density of 4-point fluid, pipe inner wall, 1 mm to inner wall, and 1 mm to outer wall in this direction were calculated. And the stress PSD graphs and the stress PSD of 2 points, 1 mm to inner wall and 1 mm to outer wall in this direction were calculated. And for the temperature PSD graph, we can find in the 2-layer composite material, due to the participant of high thermal resist ceramic, the power of temperature fluctuation decreased. And in the 1 mm to outer wall, it won't even have temperature change, while the 8-layer FGM case has a gradually decreased fluctuation power from fluid to pipe. However, in the stress PSD graphs, although there is no fluctuation in the temperature in the 2-layer composite pipe at the 1 mm to outer wall, the stress has the same fluctuation power as the point 1 mm to inner wall. On the other side, the FGM perform just like the homogeneous material while lose the vibration amplitude. So with the stress time history in the pipe, by using the ring flow counting method, the number and amplitude of fatigue cycles could be determined. For example, after the counting progress, the fatigue stress cycle is represented as circle in this graph. It indicates the stress cycle began from which stress and ended at which stress. Therefore, the stress cycle near this line is no risky cycle, while those red marked cycle are high risky stress cycles. And because we already know the 30-degree has largest fluctuation power, therefore the stress cycle on these 2 points at the 30-degree direction on the 0.5D and 1D surface are counted. The summary of mean amplitude of stress cycle is listed here. And we can find by introducing the thermal resistance dynamic to the pipe. Due to the decrease in the temperature change, the mean amplitude of the stress cycle is become smaller. And the 2-layer composite pipe has the lowest stress cycle amplitude. It shows with the same volume fraction of material, composite material has the best heat resistance performance. And FGM needs more ceramic component for completing the same thermal resistance effect. And then let's look into how the stress cycle exists in those 0.1 mm to the inner wall. It can be found easily. There are more risky stress cycles happened at the 1D cross section. And compared with the 1-layer homogeneous pipe and 8-layer FGM pipe, although the 2-layer composite pipe have the lowest stress cycle amplitude, it would generate the more risky stress cycles than other 2 cases. And here is the stress cycle at the 0.1 mm to outer wall. And compared with the cycle near the inner wall, the stress cycle are generally smaller near the outside wall. And most of the cycles have the smaller amplitude because they are close to this line. However, it's easy to find the 2-layer composite pipe has many risky cycles than other 2 cases near the outer wall. It shows the FGM pipe could restrain the stress cycles better than homogeneous and composite pipe to some extent. And here is a summary for today's presentation and some future work. The layered model was used to simulate the FGM in conventional FEM software, and the feasibility was proved. It shows the N-layer model could represent the behavior of FGM wear. And with layered model, the conjugate heat transfer in T-junction pipe and transient structure simulation were conducted. on the spectral analysis in T-junction pipe. Both in the temperature and the stress, the 6 Hz component has the largest fluctuation power. And by counting the thermal stress cycles from simulation result, FGM pipe has the ability to reduce the number of risky stress cycles from the thermal striding. And the next, we want to find an optimized graded way to increase the thermal resistance effect. With current n equal to 1 graded index, the 2-layer composite pipe has better thermal resistance effect. And we want to use the damage model to evaluate the fatigue life of FGM pipe in the future. And that's all for today's presentation. Thank you for your listening.
Thanks, Ji, for giving us an interesting talk. If there's any question, please raise your hands or type your question in the chat. If there is no question, we're a little bit behind the schedule, so we will move into the next speaker. Next speaker is Seung-hyun Lee from Gyeongsang National University. Seung-hyun will be talking about thermal performance evaluation of treated carbon nanotube bulky papers for use as a thermal interface material.
Hello, I'm Master Degree of Graduate School Seung-hyun Lee from Gyeongsang University. I will be presenting on a study thermal performance evaluation of treated carbon nanotube bulky papers for use as a thermal interface material. As the contents, introduction, experimental details, resultant discussion, and conclusion. First is an introduction. Full TIM thermal interface materials are used to aid thermal conduction between mechanically weighted surfaces such as a heat sink. When two materials come into contact, the heat conduction decreases due to the air gap formed on the surface. As shown in the figure 1, by using a material with good thermal conductivity, the resistance generated by air gap is reduced. We selected vertical carbon nanotube as a thermal interface material. Vertical CNT has many properties, and among them, we have focused on the reason that appear on the screen. Vertical carbon nanotube has excellent thermal properties and is a good component for thermal transport. They conduct heat by the vibration of the covalent bonds and carbon atoms. The stiffness of carbon bonds transmits vibration to the entire nanotube and show excellent thermal conductivity. These properties are decreasing thermal resistance formed by air gap. And we added cellulose nanocrystal to CNT-based bulky paper. Cellulose nanocrystal has strong strength. It can improve durability and reinforce heat conduction, and good compatibility with other materials. Next is experimental details. These are samples that have been tested. A total of 5 bulky paper samples were made. The first sample is untreated CNT. Second, oxidized CNT using sulfuric acid, nitric acid, and hydrochloric acid. Third, in the second oxidized CNT added to CNC 0.06 weight%. Fourth, on the oxidized CNT added to CNC 0.08 weight%. Lastly, on the oxide, CNT added to CNC 0.1 weight%. This slide bucket paper manufacturing process. First, dispersion virtual CNT. To disperse each sample, the trial process was applied for 1 hour, followed by ultrasonication for 2 hours. Second, filtration. Distilled water is filtered through the dispersed nanofluid using a vacuum filter, leaving only the virtual CNT particles. Lastly, the filtered virtual CNT is dried for 1 day and separated from the membrane filter. Then, the bucket paper was completed. The ASTM D5470 equation was used to calculate the thermal resistance value. D5470 is a test method that uses the thermal equilibrium method to determine the thermal conductivity of the material by using the law that the amount of heat flowing through the sample is the same before and after. As shown in the figure 5, we drill 6 holes in 2 copper blocks, including the surface of the copper block, insert the thermocouple and see the temperature change. This equation keeps heat on the top and cold on the bottom. When the temperature of the copper block reaches a steady state, we use the temperature to find the thermal resistance value. Figure 6 is experimental setup. A copper block was wrapped with an insulator for an experiment. And on the right, each bucket paper sample was put between the copper blocks. In all experiments, a weight of about 2 kg was applied. Next slide is resultant discussion. It is a graph of sample when the steady state is reached. Figure 7 is show temperature graph of respective channels. CNT bucket paper untreated showed a thermal resistance value of 1.526. Next, the thermal resistance value of the oxidized CNT was 1.340. From here, a graph is shown for concentration of CNC added to CNT. The resistance value of bucket paper with 0.06 weight% of CNC added is 1.217. The resistance value of bucket paper with 0.08 weight% of CNC added is 1.196. Lastly, the thermal resistance value of the bucket paper manufactured by adding 0.1 weight% CNC was 2.508. These values are shown in the table on the next slide. Looking at the table, it can be seen that a thermal resistance value of oxidized CNT is lower than that of raw CNT, and the thermal resistance value is lowered by adding a certain amount of CNC to it. When 0.1 weight% of CNC was added, the durability of the bucket paper was good, but the resistance value was not good. When comparing the 5 samples, it was found that the thermal resistance value was the lowest when the amounts of CNT and CNC were the same. Thermal conductivity may vary slightly depending on the thickness of the sample. Last of all, the conclusion. In this study, a thermal conductivity measuring device was manufactured to test the thermal conductivity of various treated multi-wires carbon nanotube-based bucket paper. The calculation of the thermal resistance value is ASTM D5470 has been conducted. The result of the calculation showed that the thermal resistance value is lower due to the removal of impurities during the oxidation treated of CNT. Besides, where the same amount of CNC was added as CNT, it was confirmed that the resistance value decreased. In conclusion, we show that CNT-based bucket paper has low thermal resistance value, is eco-friendly, and easy to install compared to conventional heat dissipating materials and can be alternative materials as thermal interface material. This concludes the research presentation. If you have any questions, please send them to my email. Thank you for your listening.
Thanks, Singhyun, for giving us an interesting talk. Is there any question? You may type in the chat. I have a question. Is Singhyun is on this Zoom session right now, or I don't think she's on this Zoom session right now. So we'll be moving to this next speaker. Next speaker is Kwon-hee Cho. Kwon is from Chungnam National University, and Kwon-hee will be talking about a study on the effect of Mg loaded on activated carbon and the process for enrichment and regeneration of ammonia.
Hello, I'm Kwang-hee Jo. I'm in the master degree at the Chungnam National University, Professor Kang Bok-i's lab. I give a presentation on a study on the effect of magnesium loaded on activated carbon and the process for enrichment and regeneration of ammonia. Contents are in the order of introduction, experiment, results and discussion, conclusions. Hydrogen is in the spotlight as a major energy carrier due to concerns over increasing environmental problems caused by fossil fuels. Among them, ammonia has been identified as one of the attractive and feasible hydrogen-laden chemicals. Also, ammonia is widely used in fertilizers, refrigeration, petroleum, chemical, and other industries. However, the Haber-Bosch process now accounts for 90% of the world's ammonia production. This process demands high pressures and temperatures. In addition, ammonia production emits large amounts of carbon dioxide due to the use of natural gas. As an alternative to this, the electrochemical ammonia synthesis method is an eco-friendly process. It It does not emit carbon dioxide because of reacting nitrogen and water at atmospheric pressure and low temperature to produce ammonia. However, the concentration of ammonia produced at low conversion rate is very low. Therefore, it may be an alternative to obtain high concentration ammonia by adsorbing low concentration ammonia produced in the electrochemical ammonia synthesis method. In this study, activated carbon was selected because it is porous material and abundant. Considering the manufacture of metal-loaded carbon so that it can be stable at heat with repeated adsorption and desorption. In metal selection, magnesium is chosen as the metal and chloride as the precursor. Magnesium chloride absorbs a total of 6 moles of ammonia per 1 mole and is a complete reversible reaction. It has a relatively low enthalpy of desorption, so it has already been studied as an ammonia storage material in many studies. However, it is not suitable for use with an adsorbent due to the slow reaction rate. Therefore, in the previous hour study, we used it as an adsorbent by increasing the surface area by impregnating magnesium chloride on activated carbon. In this study, the optimal magnesium loaded amount for ammonia adsorption was selected, and the optimal process was selected in the TSA, PSA, and PTSA processes, and multi-cycles were performed. 3, 5, 7, 10, 50, and 20 weight% magnesium were attached to activated carbon by sonication impregnation method. Activated carbon with nothing impregnated was named AC, and thus with 3 weight% magnesium impregnated was named AC-MG3. The ammonia adsorption test was carried out as a breakthrough test for TSA, PSA, and PTSA processes, and the breakthrough test conditions are shown in the table below. As a result of the BT analysis, the surface areas and pore volume of samples tend to decrease when magnesium was impregnated. However, the reduction in surface area and pore volume is insignificant when the amount of magnesium impregnated is more than 10 weight%. In addition, the average pore size was constant for all adsorbents. As a result of TJ analysis, AC showed a rapid weight loss at 480 degrees, leaving a final 0.67 weight% residue. On the other hand, the final weight of the magnesium-loaded ACs are higher than that of AC, so we could confirm that the metal was successfully impregnated. Weight loss of magnesium-loaded ACs begin at lower temperatures than AC. Nevertheless, It was confirmed that all adsorbents were thermally stable up to 360 degrees. SEM analysis was performed to confirm the surface morphology. AC confirmed a smooth surface and small particles were identified in magnesium-loaded ACs. These particles are clearly visible as the loading of magnesium increases. In particular, the low surface can be seen from ACMG10. As a result of EDX, it showed a magnesium weight percent consistent with the amount of magnesium impregnated to ACMG10. However, the magnesium content in ACMG15 and ACMG20 was 11.37 weight percent and 11.92 weight percent respectively, and the maximum amount of magnesium that can be loaded is 10 weight percent. As a result of elemental mapping, magnesium and chloride were uniformly distributed on the surface of the activated carbon. It was confirmed that the distribution of magnesium and chloride was similar, so that they were impregnated in the form of magnesium chloride. In particular, the orange circle of ACMG20 suggests that the dispersion of magnesium and chloride is similar. Through NH3-TPD analysis, the amount of desorption was calculated at 30 to 200 degrees C. ACMG20 is 2.758 millimole per gram of desorption capacity, and it is 17 times higher than AC. ACMG15 and ACMG10 showed similar amounts of desorption within the error range of 2.733 millimole per gram and 2.674 millimole per gram respectively. Ammonia desorption capacity of the adsorbent was in following order: ACMG20, ACMG50, ACMG10, ACMG7, ACMG5, ACMG3, AC. In order to confirm the optimal amount of magnesium loaded for ammonia adsorption at atmospheric pressure and high pressure, it was performed in the TSA and PSA processes. And the adsorption capacity is shown in a table. And magnesium chloride powder showed the lowest adsorption capacity due to the low reaction rate with ammonia. ACMG10 had the highest average adsorption capacity of 2.461 millimole per gram in the TSA processes and 1.298 millimole per gram in the second cycle of PSA process. Therefore, the optimal amount of magnesium impregnated for ammonia adsorption was determined to be 10 weight percent. The highest ammonia adsorption capacity, ACMG10, was performed in the PTSA process, which was reabsorbed after desorption at a mild temperature of 100 degrees C. It showed an adsorption capacity of 2.769 millimole per gram and a regeneration rate of about 68% compared to first cycle. It was confirmed that ACMG10 could be used in TSA, PSA, and PTSA processes. After desorption at 100 degrees C, readsorption was repeatedly performed 20 cycles. Average of adsorption capacity showed 2.783 millimole per gram. Even with repeated adsorption and desorption, thermal stability and activity stability were confirmed without lowering the adsorption capacity. The conclusion is that magnesium-loaded AC was synthesized by varying the amount of magnesium impregnated using magnesium chloride. The maximum loaded magnesium was confirmed to be 10 weight% throughout EDX. From ammonia TPD, TSA, and PSA research, ACMG10 was identified as the most optimal adsorbent for ammonia adsorption. ACMG10 shows high regeneration when desorption and readsorption at a mild temperature of 100 degrees C, and its applicability in TSA, PSA, and PTSA process was confirmed. As a result of the multi-cycle, thermal stability and activity stability were confirmed. ACMG was confirmed as a good adsorbent in the ammonia concentration processes. Thank you for your attention.
Thanks, Kwang-hee, for giving us an interesting talk. If there's any question, feel free to type or raise your hands. I have one question. Other than controlling the weight percent of magnesium, what other parameters can be controlled to increase the absorption of ammonia? 네. You can answer by typing in the chat. I think the Kwang-hee's microphone is not connected. So we'll be moving to next speaker. Next speaker is Ah-jung Lee. Ah-jung Lee is from Gyeongsang National University. And Ah-jung will be talking about carbon nanotube cellulose nanocrystal composite bucket paper, functionalized with various methods for improved hydrophilicity, performance, and behavior. You may start.
Hello, I am master degree of the graduate school Ajang Lee from Gyeongsang National University. I will announce of the carbon nanotube cellulose nanocrystal composite bucket paper functionalist with various methods for improved high velocity, performance, and behavior. Let's start it. As the contents, introduction, experiment details, result analysis, and conclusion in turn. First of all, introduction. The introduction part will be shown about the respective materials, what it is, how it works, or how it look like, something like that. The first one is carbon nanotube. Carbon nanotubes are most important material in my paper. Researcher as various application has studied CNTs. It can be used for biologic electrodes or Catholic even medicine side. So this material characteristic is chemical bonds of carbon nanotubes are composed of goodly strong sp2 hybrid bonds to provide unique strength electrical properties by pi bonds and high thermal conductivity around the tube axis as sp2 bonds. So, and we expected good body properties such as thermal conductivity, electrical conductivity, and as you can see that it has a really unique structure. Also, if the workers or researcher do chemical reaction for the attach the functional groups, it can be developed more powerful material as you want, and it's gonna affect which can control their performance as you want. And we picked the virtual CNT because it is cheaper than the singular CNT, so it's excellent economically. And also, we can produce the sheet or paper by this virtual CNT, which is called it bucket paper, like figure 2. The bucket paper is produced by untangled carbon nanotube like this, and has excellent durability and can be used as a TIM material. Second of all is cellulose nanocrystal. This material has a high aspect ratio and hydrophilicity characteristic of structure that is effective to good disposability. Thus, it has structure advantages such as excellent mechanical properties like low density. So it was from the cellulose, and we can obtain the isolation of the cellulose by acid hydrolysis, usually using the sulfuric acid nowadays. Also, it is composite of OH functional groups, so it has excellent hydrophilicity. I was expecting this performance from OH functional group. In summary, it is low density, high strength, and elasticity, eco-friendly because it came from wood or tree. And last goodly property is hydrophilicity from the OH functional group. And third, I will explain which is used the measurement to experiment the word angle for hydrophilic or hydrophobic. The contact angle is an optical measurement of the standard use drop shape that is measured to know fluid characteristic as a hydrophobic or hydrophilic. In the static contact angle, the diffuse drop lies on the surface of a solid, like baseline. So, as you can see, if the drop shape bigger than 90 degree, it's a hydrophobic, and smaller than 90 degree, it can be say hydrophilic characteristic. So next one is experiment details. The first explanation is about the how manufacture the various nanofluids before the manufacturing bucket papers. There are two ways for modifying virtual CNT surface. First of all is using the nitric acid, sulfuric acid, hydrochloric acid, like figure 5 is using, so we call it that oxidized virtual CNT, namely OCNT. Second of all is using potassium persulfate and NaOH, like figure 6. We called it that alkalis virtual CNT, namely ACNT. One can introduce functional groups to the CNT surface and tube. So oxidation is easy to handle and a common method. The alkalization is eco-friendly and more simple method. So we will compare the bucket paper produced by these two methods with the pristine bucket paper. The case of the pristine virtual CNT do nothing, just only ultrasonicated for a minute because we need to focus their own performance so that the simple dispersion methods for like ultrasonication. So we also added the CNC to improve the durability that virtual CNT alone lacks. The most to look forward to be how the hydrophilicity of the CNT with the leach OH groups will work. After this method, we manufacture in a nanofluid condition for bucket paper as figure 8. Then this solution is filtered to produce bucket paper. Before the contact angle measure, we need to adjust them because first it is too big to experiment the wall drop because wall drop going to suck it in between tubes. So we consider that impact the result. So there are the reasons for the accuracy of the contact angle to prevent supersaturation of fluid absorption on the surface for the application of miniaturization. So people the contact angle, so we just adjusted their size like 77 millimeter to 10 millimeter, like figure 9. So next one is result and analysis. You can check each. This is everyone is bucket papers. So you can check each bucket paper like send image. CNC there is 2. A is alkalis bucket paper. B is low type. C is oxidized type. When comparing each, low CNTs did not undergo any oxidation or alkalization, so impurity and unstable tubes won't exist. By the way, figure A and C doesn't have impurity and unstable tubes and low CNT, so we can say that oxidation and alkalization not only assist remove the impurities but also have durability when manufacturing bucket paper. There's impurity, like look at the figure point B. And next, and we can check each tube condition by the temp image. Unlike low CNT that contains impurities, the figure C, it can be seen that the inner surface is clean and the tubes are TD like figure A or and B. the chemical treatment stands out dispersibility too. Look at the figure 20 and 13. The chemical treatment stand out in dispersibility or dispersion. It shows improved dispersibility and stability compared to low CNT by UV test. When CNC is added, the dispersibility tends to be further improved. Increasing dispersion is the impurities, and the van der Waals force are controlled through the chemical treatment. And electrical conductivity improved with the CNC. This means seamless interaction between CNT and CNC. Last of all, we should check how to work the chemical treatment on the tube surface that is attached to the functional group or the check damage to the tubes. We did the FTIR and Raman spectroscopy. Look at the figure 50. You can see everywhere that the peak value has rise after chemical treatment. The point to be noted here is when comparing oxidation treatment and alkalization treatment. In the case of oxidation, it can be seen that the OH group appears less stretch, and in the case of alkalization, it can be seen the stretch of CC double bonding is remarkable. Figure 60 is a Raman spectrum. It is divided into D band, G band, and G band. The values of ID divide IG for the all CNTs are larger than for low CNTs, the largest ratio being observed for all CNT. But there was different trend is observed by alkalization. The ratio of the D band, DN, or G band, the chemical surface modification in this breeze depends in the virtual CNT structure. But as you can see from 10 images which have the smaller defects ACNT than OCNT, therefore compared to low CNT and ACNT with clean impurity has a small value, and low CNT with impurity has a high values. In addition, it was compared that OCNT, which was attacked by a strong acid, had the largest damage to the tube. The last one here is the smaller the value is small value is the more hydrophilicity. So bucket paper with the best hydrophilicity is manufactured with OCNT with the CNC at 43.7 degrees. Secondly, the alkalization CNT and with CNC are combined. CNC manufactured the bucket paper, and the hydrophilicity is increased by more than 1.5 times compared to the case of not adding with the CNC. Also, in the case of pristine CNC bucket paper, since it was not affected by surface modification, it showed a strong hydrophobic tendency of more than 90 degrees. The next one, last our conclusion. So, alkali treatment assists to modify the surface of the CNT tubes, and it shows high hydrophilicity due to the introduction of functional groups. Oxidation treatment assists to modify the surface of the CNT tubes, but it could be compared that the tubes were damaged due to a strong acid attacking. It shows high hydrophilicity due to the introduction of functional groups as alkalization. In the chemically treatment material CNT, the presence of the functional groups could be determined. It can be seen the variation in chemical composition that only improves dispersion but also improves stability and electrical conductivity. By adding CNC as a dispersibility is improved, also stability and electrical conductivity. The hydrophilic performance could be further developed through the OH group, which is unique chemical composition of the CNC. In addition, the hydrophilic property of material CNT, which were not originally processed through chemical treatment, and the interaction with CNC can further enhance the hydrophilicity properties. So the bucket paper with hydrophilic performance will be excellent material for application with carrying nano-sized hydrophilic or microsurface. So thank you for listening my presentation. So, and if you guys have some question, let me know below the email address. So thank you for attention me.
Thanks, Ajong, for giving us an interesting talk. Ajong is not currently online, so we will be moving to next speaker. Next speaker is Matthew Bolchi, but he's not currently online as well. So we're moving to the speaker, Singa Pak. Singa Pak is from Gyeongsang National University. He'll be talking about heat transfer enhancement of aluminum oxide water nanofluid by adding anionic surfactants in a heat pipe.
Hello everyone, my name is Singa Pak. I'm one of the PhD students in the department. In this presentation, I'm going to talk about heat transfer enhancement of aluminum fluid by the anionic surfactant in a heat pipe. I prepared 6 sections. A common problem in electronic device is managing summer conditions for optimal efficiency. Fundamentally, we can divide the cooling technique into 2 categories: active cooling system and passive cooling system. Active cooling refers to cooling technologies that rely on external device to enhance heat transfer. Active cooling system includes forced convection through fans or blowers, which can be used to optimal thermal management. The disadvantages of active cooling are that it requires the use of electricity and has a size limitation. Passive cooling utilizes nature, conduction, convection, and radiation to cool a component. Passive cooling system includes heat pipe and heat sink, both of which utilize fundamental heat transfer principles. The advantages of passive cooling techniques lie in the energy efficiency and lower cost, financial cost. Heat pipe has many factors affecting heat transfer performance. I control three factors: properties of working fluid, filling ratio, and heat input. Working fluid includes nanofluid. Nanoparticles was chosen as aluminum. And I focused on two different working fluid properties: thermal conductivity and surface tension. Aluminum nanoparticles are widely used in many applications: biotechnology, publishing, material science, and heat transfer. Surface tension and thermal conductivity of aluminum fluid with different type of surfactant were measured to identify the effect of surfactant. As you can see the figure 4, aluminum fluid with SDBS surfactant had the lowest surface tension, followed by with LB and then with SDS. Although the aluminum fluid added surfactants were significantly decreased than that of aluminum fluid without surfactants, regardless of the type of surfactants. SDS could decrease the surface tension of aluminum fluid the most. And it is clearly observed that the addition of surfactant decreased the thermal Pulleys with SDBS had lower heat transfer coefficient than distilled water in case of 30% of filling ratio. However, the pulleys with SDBS have similar or higher heat transfer coefficients than distilled water in case of exceeding 30% of filling ratio. In conclusion, all kinds of surfactants substantially reduce surface tension of aluminum nanofluid, especially aluminum nanofluid with 1.5 weight% of SDBS has the lowest surface tension. It was confirmed that the nanofluid with only alumina has the highest thermal conductivity, followed by the nanofluid with LB, with SDS, and with SDBS. In other words, the thermal conductivity of aluminum nanofluid decreases with the addition of surfactants. It was revealed that the thermal conductivity of aluminum nanofluid was decreased with the addition of surfactants. In particular, aluminum nanofluid added 1.5 weight% of SDBS showed the lowest thermal conductivity. The heat transfer performance of the heat pipe with solution added 1.5 weight% of SDBS could be improved in case of filling ratio exceeding 30%. When the heat input was 15 watts, the effect of reduced surface tension on heat transfer performance of heat pipe obviously appeared. Thank you for your attention.
Thanks, Singyup, for giving us an interesting talk. Singyup is not currently online, so we'll be moving to next speaker. Next speaker is Katsushelo Lilis Moiri. He or she is from University of Pretoria. The title is Recovery and Synthesis of a Dimetal Composite from Acid Mine Drainage and its application for the removal of hexavalent chromium and Congo red dye from wastewater. You may start.
Good day, everyone. My name is Katsushelo Miedi from the University of Pretoria in South Africa. Today, I will be presenting on the recovery and synthesis of a dimetal composite from acid mine drainage and its application for the removal of hexavalent chromium and Congo red dye from wastewater. This is my presentation outline. I will start by introducing acid mine drainage and its benefits and impacts. I will then talk about minerals recovery and the processes involved. Thereafter, I will talk about how chromium and Congo red dye are two of the major pollutants of water. Then I will talk about the treatment technologies that have been studied and explored for the treatment of acid mine drainage, chromium, and Congo red dye contaminated water. I will then move on to the aim and objectives of the study, the materials and methods that were adopted. I will then discuss the results that were obtained, conclude, and make recommendations. Mining significantly contributes towards gross domestic product, job creation, and poverty alleviation. However, on the other hand, it has been reported to pose serious environmental impacts. This is attributed to the end products that are generated from the mineral extraction processes. For example, one of the major products of mining is acid mine drainage, which contains toxic chemical species such as iron, aluminium, manganese, sulfate, amongst others, which are the major components of AMD. The other components of acid mine drainage are in traces, and that include heavy metals such as arsenic, chromium, zinc, just to name a few. As such, this effluent needs to be treated prior release into the environment because it contains toxic chemical species. However, a number of technologies have been studied and employed in the treatment of acid mine drainage, but secondary pollution has been an issue of prime concern as there are disposal costs that are associated with the management of toxic chemical species, which then become a serious environmental concern. Hence, we refer to it as secondary pollution. This also contributes to incurring of additional costs. Well, that's where the United Nations Sustainable Development Goal Report comes in, which advocates for circular economy in waste beneficiation, thereby moving away from waste disposal. Different studies have been focusing on value recovery and valorization. In value recovery, we talk about minerals that are recovered through different technologies such as precipitation, adsorption, filtration, coagulation, just to name a few. This study opted for selective precipitation in the recovery of dimetal composite from authentic acid mine drainage. Different studies have reported that aluminium and iron have strong affinity to chromium, and the techniques thereof have been successfully employed. Hence, this study aimed to recover aluminium and iron as a dimetal composite from authentic acid mine drainage to remove chromium and Congo red dye from wastewater. Chromium is a heavy metal with prime states of +3 and +6, of which +6 is the most toxic. Ecotoxicological impacts associated with chromium have been reported to be teratogenic, carcinogenic, and mutagenic. On the other hand, Congo red dye is an anionic dye mostly used in textile, printing, and plastic industries, and its ecotoxicological impacts include the impairment of water quality as well as teratogenic, mutagenic, and carcinogenic. That is why it is important for these pollutants to be removed from water for the protection of the environment and human health. Some of the studies reported for chromium and Congo red dye removal include adsorption, filtration, biosorption, etc. This study focused on adsorption as the removal technique of chromium and Congo red dye from wastewater. This study was governed by the following aim and objectives, of which the overall aim was to recover and synthesize a dimetal composite from authentic acid mine drainage and explore its application in the removal of hexavalent chromium and Congo red dye from wastewater. In order to achieve the overall aim of the study, the authors had to come up with objectives, of which the first one was to recover dimetal composites from raw acid mine drainage. The second objective was to employ different pre-treatment techniques to enhance the reactivity of dimetal composite. The third objective was to optimize conditions that are suitable for the removal of chromium and Congo red dye using the synthesized dimetal composite. The fourth one was to characterize the dimetal composite before and after adsorption. The fifth one was to compare the product water quality at optimized conditions with the World Health Organization water quality standards. In order to achieve the outlined aim and objectives, the following materials and methods were used. Iron-rich AMD was collected from a coal mine in South Africa. Chromium-6 and Congo red dye solutions were simulated for optimization experiments. The dimetal composite was recovered and synthesized via selective precipitation. For the adsorption of chromium-6 and Congo red dye, a batch experimental approach was adopted where concentration, pH, agitation, time, temperature, and dosage were optimized. FTIR, SAM, EDX, TGA, and BET were used for the characterization of a dimetal composite before and after adsorption. As reflected in the table, AMD characterization results showed that the raw AMD is rich in iron, aluminium, manganese, and sulfates, and this made it viable for the recovery of iron and aluminium dimetal composites. SAM and EDX-EDS show the surface morphology and the elemental composition of the recovered and synthesized dimetal composite, respectively. From the elemental composition, we see the presence of iron and aluminium recovered from raw acid mine drainage. The FTIR shows the functional groups that are in the composite, and we see the presence of hydroxyl group and water. The BET shows the surface area and porosity of the compound. The BET shows the surface area and porosity of the composite, where we see that the surface area of the material is 24.62 square meters per gram, while the TGA gives the stability in the thermal sense of the material. Optimization results of adsorption revealed that 50 milligrams per liter of chromium concentration was found as the maximum concentration that the material could absorb before oversaturation, while 100 milligrams per liter of Congo red dye was the maximum concentration the composite could take. Moreover, 3 grams and 0.5 grams were the optimum doses of the material required to remove these concentrations of chromium-6 and Congo red dye respectively. The optimum agitation time at which chromium and Congo red dye could be removed from the solutions was 180 minutes and 20 minutes respectively. When studying the effect of pH, we observed that the optimum pH for the removal of chromium-6 was at pH level 3, while Congo red dye could be greatly removed between pH levels of 3 and 8. As for the effect of temperature, the highest percentage removal of chromium-6 and Congo red dye were observed to occur at 45 degrees Celsius and 35 degrees Celsius respectively. After the adsorption process of chromium-6 and Congo red dye, we observed the presence of new functional groups and the shifting of bands. For example, the presence of sulfur trioxide was observed after Congo red dye adsorption took place because of the presence of sulfur in the dye. Adsorption kinetics for both chemical species followed pseudo-second order as opposed to pseudo-first order. As depicted in the pictures, we see that the surface morphology was also observed to have changed after chromium and Congo red dye adsorption. The presence of chromium and sulfur is observed in the EDX-EDS spectra, which clearly shows that adsorption did take place. The EDX mappings also show the presence of chromium and sulfur from Congo red dye after adsorption. Iron aluminium dimetal composite was successfully recovered and synthesized from acid mine drainage through selective precipitation, and its efficiency was tested through adsorption of hexavalent chromium and Congo red dye on a batch experimental approach. The material successfully removed more than 95% of chromium-6 and more than 99% of Congo red dye from wastewater at optimized conditions. A regeneration study showed that the material can be efficiently used more than 4 times on the adsorption of chromium-6 and Congo red dye. Future recommendations and research avenues include the fabrication of a fixed bed reactor for a continuous process, as well as research that will focus on harnessing the regenerates. Moreover, the authors will explore viable options of valorizing the regenerates. The authors acknowledge and appreciate the following organizations and people. Thank you.
Thanks for giving us an interesting talk. If there is any question, please raise your hand or feel free to type in the chat. I have one question. As well, I was wondering how is this experimental setup is done to measure the absorption of chromium in the batch. Could you briefly explain?
Hello. Okay. The experiment was conducted on a batch setup, and the chromium analysis was done through ICP.
Okay. Is there any other questions? If there is not, the next speaker is not currently online, so we'll have to wrap up this session. So all presentations are finished, so we're now closing the session. Thanks for attending and participating this session. Keynote session will be starting here at 10:45 a.m. So please stay for a very interesting talk by Professor Kon Young-an, Professor Bruce Dunn, and Professor Jae Chang. Thank you again for participating in this session. Thank you.
Okay. Shall we start today's keynote session? Good morning. I am Seung-Nam Cha from Sungkyunkwan University and pleased to be the keynote session chair. In this session, we have three keynotes. Let me call the first speaker, Professor Kwon-young An from Gyeongnam National University of Science and Technology. His presentation is on the recent work on freestanding manganese oxide on graphene films for aqueous zinc ion batteries. Okay, Professor, please give a presentation when you're ready.
Yeah, I'm ready. Yeah. Good morning and hello everyone. My name is Kwon-young An from Gyeongnam National University of Science and Technology. Thank you for giving me the chance to introduce my work and our lab. Today, I will talk about the freestanding manganese oxide on graphene films for aqueous zinc ion batteries, not lithium ion batteries. Yeah, this is content. So first, I will introduce our lab. Our lab name is the Smart Energy Material Lab. So we called the SEML. So we focus the battery engineering and wearable devices, functional carbon and functional catalyst. So first is the battery engineering, and among them, battery engineering and wearable devices. We studied to improve the fundamental studies, and the functional carbon and functional catalyst is the for the industrial areas. So, and this is our lab symbol, and this handsome monkey is me, made in our student. So we are the SEML. The first is the first research topic in our lab is the lithium-ion next generation batteries. As you know, lithium-ion battery is a very popular research work in the secondary batteries. So, but our research focus the sodium-ion batteries and zinc-ion batteries. So we develop and design of the advanced materials for next generation batteries. So next topic is the wearable devices. To you can imagine in the future we use the wearable and flexible electronic devices. So we need the flexible energy storage devices. So we target to develop and design advanced materials for wearable energy storage devices. So
my background is the material science and engineering. So as you can see, I did study the various nanostructures and morphological structures and particles, nanowires, porous structure, hollow structure, cohesion structure, something like that. Yeah. So this is the general introduction. So as you know, we need the eco-friendly life. So first is the new energy, second is the renewable energy, and finally is the energy storage. So new energy is the hydro fuel cell, bio, and renewable energy are solar, wind, water, and geothermal energy. My work is the energy storage. So usually we study the secondary batteries. So energy storage is the key part for eco-friendly our life. So this is the trend of energy storage devices. First, we did use the portable devices such as smartphones, laptop, camera, and robot cleaner. Among them, robot cleaner is recently robot cleaner is a very good item for our life. So I recommend the robot cleaner using the battery. So, and transportation and power system. So as you know, Tesla and Hyundai, they have an electric car for transportation. And so we need the, also UPS and CS we use to continue the renewable energy. And we need the many requirements such as high energy density, high power density, long cycle, and low cost. So we need the advanced technologies for energy storage. This is the typical secondary battery. This is the lithium-ion battery. As you know, we have many professional battery guys, and lithium batteries converts from chemical energy to electrical energy. They have a main component, anode, cathode, electrolyte, and separator. So we can see the applications, smartphones, laptop, robotics, ESS, and electric bicycles. But I'm junior, but as you know, we have a lot of professional battery guys, lithium-ion batteries. So I think that what is the next battery? What is in our life? You can remember the blah blah smartphones. If you have a blah blah smartphones, we can not take the airplane because of very dangerous of the lithium. So also this map is shows the limited source of lithium. We have not lithium source in our country, and very few countries have the lithium source. And so we can see the increasing cost of lithium. So I think that what is the next battery? What is my work? So we need the exploration of other batteries. Yeah. So I think that zinc ion battery is the number of secondary battery system that storage and release energy through repeated induction and interaction reactions of zinc ions. So very similar structure to lithium-ion batteries, but in this battery we use the zinc metal, and the cathode is the manganese oxide and vanadium oxide. Also, we use the aqueous electrolyte, not organic electrolyte. So, advantage of zinc-ion batteries, first is the safety. It is the very safety of zinc. So also eco-friendly and compactness, high theoretical capacity, low cost, and high energy density. So they have a lot of advantages. So I think that, zinc-ion battery is a good candidate for next generation batteries. So this slide shows the theoretical capacity of lithium, sodium, magnesium, calcium, zinc. You can see that high volumetric capacity of zinc, very high compared to other lithium, other source. So this means it is a good candidate for large scale ESS energy storage system because of high volumetric capacity. As you know, a few years ago, we have a big issue for ESS problem because of lithium. So I think that zinc is very nice and friendly to our life, in our life. Yeah, so as I told you, today I will talk about the zinc ion battery. So among them, the focus is the cathode materials, manganese-based oxide. So zinc ion batteries had two typical cathode materials. First is the manganese oxide, and second is the vanadium oxide. So we called that MnO2. MnO2 have a good advantages as a low cost, eco-friendly, good cycling stability, but they shows the low theoretical capacity and low electrical conductivity. And so also MnO2 have a different phase, alpha phase, beta phase, gamma phase, something like that. So among them, I studied the alpha phase MnO2. This is the tunnel structure with the 2x2 structure. So you can see the tunnel structure alpha MnO2, and this area, tunnel area, is the zinc ion interaction areas. So this is the reaction mechanism of MnO2 for zinc ion batteries. You can see this is the charging process. Zinc ions move from cathode to zinc metal anode, and this is the discharging process. So this is the reversible reaction mechanisms. You can see this detailed information for cycling reactions. So among them, key is the two electron reactions for zinc ion. For zinc ions, so zinc ion batteries has a high energy density. So, and I will talk about my work. This is the experimental process. First, I use the graphene. Graphene is the, as you know, high electrical properties and excellent chemical, physical properties. So I use the graphene and I fabricate the graphene film and using the stacking process. So I use the graphene film it is the current collector, both the current collector and the substrate for manganese oxide. So this process is the, you can see this process, and I obtained the needle structure MnO2 using the KMnO4 solution. So this is the SM image and TEM and photograph of graphene. A and B, you can see the some microstructure of graphene, and C and D means the high quality of graphene. So also, we did achieve the large scale process of graphene film. But as you know, graphene is graphene has the high chemical stability. So if you want the growth or some design of the design with the other materials, we need the functionalization process of graphene on the surface. Because of carbon and carbon group is very strong. So we did the functionalization process using the HCl. So you can see this is the Raman spectra. You can see the D and G band. Also, right side is the contact angles. So after functionalization, we can see the low contact angle. So this is the SEM image of after growth process. As you can see, 1 hour. You can see that this box. This is we use the HCl and KMNO reactions. So we obtained the needle-like structure on the graphene surface. So among them, 1 hour is the optimized condition. So you can they have a uniform structure and the nano-sizing structure. So this is the cross section of electrode. It is the very hard to obtain the cross section of the electrode. You can see the graphene film. It is the graphene film is the current collector and the substrate rate for MNO. So MNO is the very nano-size structure on the surface. So as I told you, we needed the functionalization process of graphene. This is the this same is the without the functionalization process. So the poor surface wettability of the bare graphene cannot use the substrate for electrode. So functionalization process is keep layer. This is the TM image, so we can find the needle structure and the alpha phase MNO. So you can see the EDS result. We found the Mn and O elemental source. So this is the physical and chemical properties of our electrode for cathode. A is the TGA result. You can see the very small amount of manganese oxide, and B is the means the graphene, graphite of graphite structure, and C and D shows the MNO XPX signal. So this is I will show you the electro chemistry result. So A is the nice kit plot. We obtained the EIS result. So as you can see, pink line is the optimized cell. So they have a excellent zinc ion diffusion ability. You can see the A and the B, C. So EIS result means the excellent electrical conductivity and excellent zinc ion diffusion performance. So this is the battery performance at the different current densities. A is the, you can see the A, pink line is the very high specific capacity, even the high current density. So you can see the B, pink line is the high capacity in the overall current density than other MNO-based zinc ion batteries. So she is the first is the almost 100% Coulombic efficiency. It is the good reversible reactions, and the optimized battery is the high good cycling stability with the high specific capacity. So why this is the best energy storage performance of optimized electrode? The first is the high electrical conductivity, because this is without the insulating binder. And the second is the uniformly freestanding MnO2 structure with a large electroactive site and with the improved zinc ion properties, diffusion properties. So this is the SEM image of optimized electrode after cycling test. So you can see the initial needle structure of MnO2. So you can see the separator and other structure. This cell fabricated using the aqueous electrolyte, aqueous solution electrolyte. So the morphological structure of the optimized electrode is maintained without any changes after the cycling stability test. So this is the Lagon plug. So I think that how about the performance of our zinc ion batteries? So you can see the Lagon plug optimized the battery. Zinc ion battery is the very higher energy density and high at the low power density and high power density compared to lithium ion batteries, sodium ion batteries, aluminum ion batteries, magnesium ion batteries, potassium batteries. So among them, other batteries, our fabricate zinc ion batteries show the high energy density. So next, we is the all solid state zinc ion battery, because as you know, we can use the wearable electronics such as a smartwatch, smart ear, and so we need the all solid state batteries without solutions. So we fabricate the all solid state zinc ion batteries with optimized cathode electrode and gallium electrolyte and silicon film. So this photograph is the solid state zinc ion battery. So also we did the scale up process for solid state zinc ion batteries. So as you know, some low specific capacity and energy density compared to aqueous systems, because gallium electrolyte has a high resistance interface between the electrode and electrolyte. But we have the high energy density compared to other batteries using the gallium electrolyte and solid state conditions. So also we did check the mechanical properties during the cycling test. You can see the C. So even the folded flat water and folded water, these batteries did operate the various states. So this is the photograph. We can turn on the LED in the water, and we can turn on the propeller. So we have this means that we have the high energy density, high power density, and waterproof properties in the water. So also we need the high energy and high power density to turn on the propeller, but we did it. So this is the mechanical properties, and repeating the flat and folded state is 50 times. So they have a good capacity retention, even the cycling and the mechanical test. Oh. So this is conclusion. I like a scheme to discussion conclusion. So first, we did work the binder-free and flexible cathode was cathode to use in the cathode for zinc ion batteries. So as I told you, we use the graphene, use both the current collector and the substrate to gross MNO. And next, we did functionalization of graphene film on the surface using the acid treatment. So we did obtain the uniform manganesium oxide on the surface, and we did find the optimized time to gross MNO2 on the surface. So we, as you can see, we obtained the freestanding manganesium oxide on the functionalized graphene film. So we fabricate two types of batteries using the aqueous solution system and the gel electrolyte. So also they have a good high energy density compared to other batteries, lithium-ion batteries, sodium-ion batteries. They have a good performance. So this work proves that freestanding MNOs on the flexible graphene film can provide a promising route to next generation batteries. So if you want the detailed information in our work, you can see at the Chemical Engineering Journal. So a few days ago, accept. So as I told you, we are the SEML. So if you want do you want to build a collaboration work with me, with a handsome monkey, and if you want the battery engineering, wearable devices, functional carbon, functional catalyst, anytime contact me and call me. Yes, we did work with the Younggun Lee and Jaeyeon Lee. So always thanks for our student, our lab member. Yeah, thank you for your attention and thank you for your time.
Thank you, Professor Aaron, for the very interesting presentation. Now the paper is open to question or any comments. Just a moment. Just a moment. You got the mic.
Thanks for enlightening us, Professor.
Yeah.
So I have three questions regarding to the future of zinc-ion batteries.
Yeah.
First, as I can see that these are relying on the ambient conditions. So what will happen when they will be exposed to the outside air? Will they get dry, or what will happen? And second, like they are having the flooding potential. So what about the active life? And third, are these recyclable?
Yeah, sorry, once again, please. Yeah.
So like these are relying upon the ambient condition. First question was this.
Yeah.
So what will happen when they will be exposed to the outside air?
You can means the outside reaction.
Yeah.
Oh yeah, exactly. So after cycling test of the zinc-ion battery, we did found the zinc oxide on the zinc metal. So it is the first side reaction, and the second is the destruction of MnO2 because of the insertion and interaction of zinc-ion batteries into the MnO2. Yes, we have two.
And second was related to the active life. Like they are having the flooding potential. So what about the active life of this?
Active life?
Yeah, active life.
Active life, yeah. Berries. Last year I fabricated these batteries. It is no problem. Just similar to lithium-ion battery and other batteries because of aqueous system, not organic system. So very high safety and a good cycling stability. Yeah.
And will these be recyclable?
Yeah.
Will these be recyclable?
Recycle. So it will check. Yeah.
Thank you, Professor.
Okay.
Is there any other question or comments? Paper. Okay. There is no more question. May I ask a quick question? It's very simple. Okay. Oh no. Yeah, I have one more question.
Yeah.
Zinc seems to be a very promising candidate for the future battery system.
Yeah.
Based on your talk. So could you tell us briefly what is the most difficult part or issues
Yeah.
to commercialize zinc-based battery in your future?
Yeah. So it is a good question. So zinc-ion batteries have low voltage ranges compared to lithium-ion batteries because zinc-ion battery use the aqueous system, but lithium-ion battery is use the organic system. So if we obtain the organic system for zinc-ion batteries, so it is good candidate to next batteries.
Okay, thank you.
Yeah.
Thank you very much.
Thank you.
Okay, let's thanks again to the speaker. Before starting the next presentation, we'd better to sort out the so let's have a couple of minute break. Okay, let me call the next speaker, Professor Bruce Dunn from UCLA. Professor, are you in the online? Professor Dunn? Okay, next. Okay, next speaker is Professor Bruce Dunn from UCLA. His presentation is on the recent work on creating materials for high-rate energy storage. Professor Dunn?
Yes, can you hear me okay?
Yeah.
You can hear me okay, and you can see my screen, and let me move to presentation. How is that?
Everything fine.
Okay. Okay, so first let me thank the organizers for the opportunity to come to this conference. I'm sorry I can't be there with you, but hopefully you'll enjoy the talk. So let me talk about the about our work on high-rate energy storage. The prior paper was very good because it gave a lot of background into batteries. So I won't have to do too much of that. And I can focus on the material science part of things. And that's good because this is a conference on functional materials. So what I'm going to do first is to tell you how we identify these materials. We don't want to just make these empirical. We don't want to do this in a random way. What we want to do is to be able to identify what the materials look like. And then I'll give you a number of examples of what we call extrinsic pseudocapacitance. And these are materials usually that you've made them into nanostructures or they're mesoporous, and I'll go through a few of those. And you'll see how these materials can become very good high-rate materials. And then finally, I'll demonstrate or show you a demonstration device where we are able to generate 100 watt hours per kilogram, and we're able to do that at about 5 kilowatts per kilogram, which is, again, quite good. Okay, so this tells you a little bit about that. Let me be very basic and start with just a very basic discussion about batteries and supercapacitors, and capacitors rather. And so the idea then is that, I'm going to see if I don't want to do that. I was trying to get a laser pointer, but I guess it doesn't work. So batteries involve Faradaic reactions. So there's charge transfer that occurs, and that's how the energy is stored. We're familiar with this with the various materials that we just discussed. There's a change in the valence, and you get high energy density from this. Capacitors are different. In capacitors, it's a physical process. Ions adsorb on the surface, they desorb on the surface, they form a double layer. The charge is stored in the double layer. There's not much charge that's stored, but it's very fast because the distances are very short. And so the advantage is that it's a high power device. The disadvantage is that it's low energy density. Batteries are almost the reverse. They have high energy density because of the charge transfer, but they have limited power because of the fact you have to have everything is diffusion control. So that's the other part of charge storage. Now, capacitive charge storage over the past decade has had a real increase in the quality of the materials and in the applications. We call these EDLC for electrical double layer capacitors. They have good capacitance, well over 200 farads per gram, which is quite good. They can get very high power, and that's extremely important, of course, for a number of applications. And you can put them on the shelf for a long time, and their cycle life is excellent. The disadvantage is their low energy density. And even though there's been a lot of work on trying to improve the materials using graphene, and carbon nanotubes, and various types of carbon, the fact remains that for the most part, these devices, these materials, have a low energy density of less than 10 watt-hours per kilogram. And by comparison, that's at least an order of magnitude less than any battery material. And then there's aspects of cell voltage. But anyway, the advantage is the high power. And over the years, there's been a lot of interest in high power devices. So that now these days, supercapacitors, which are these electrical double layer capacitors, they have a wide variety of applications. And that means they're going to be successful. They're very well known for doing backup power storage, UPS, but they're also involved in industrial products, robotics, and forklifts, and things of that nature. They also are in consumer electronics. And so that's another huge area. So the result of all this is that supercapacitors have over $1 billion a year in sales, which is quite good. And it's really been an increase of about 10% year after year. So it's been a very active market. But again, they don't have much energy storage. And so the question is, suppose you could combine the two. Suppose you could get energy storage and power. What would that look like? Well, this is a very nice graph. It comes from a number of years ago. In this plot, we are plotting the specific power in watts per kilogram as a function of the specific energy in terms of watt-hours per kilogram. And here's where our electrochemical capacitors are. You can see that they maybe get between 1 and maybe almost 10 watt-hours per kilogram, maybe a little bit less. But you can see that they have no problem going up to 10 kilowatts per kilogram. In contrast, for lithium-ion batteries and then some of the other batteries, you can see that they can do very nicely with well over 100 watt-hours per kilogram, but they don't go up much beyond 100 watts per kilogram. What we really want to do is we really want the best of both worlds. We want to blur the distinction between what's a battery and what's a capacitor. And we want to do that by going here. This would be the targeted area so that the material would have the energy density of a lithium-ion battery material, but it would have the power density of a capacitor material. So how are we going to get there? Well, the best thing about research is that, you have to start trying and see what's the best way. And I think it's fair to say that nobody really knows. There's a lot of work that's geared towards taking lithium-ion battery materials and increasing their power density, often by making them nanoscale, but that doesn't always work. And then there's a lot of work on taking supercapacitor materials and other carbon-based materials and functionalizing them so that you can increase the energy density, and that works a little bit, but nothing is really in this range. And so really it's a question of how do we do this? What's the best way to get there? So suppose we did. Is anybody really interested? Well, I think the answer is yes. We know that electric vehicles are just going to be more and more popular, and we know that no one wants to wait for an hour to have their car charged. And so the idea of being able to have an electric vehicle that can charge in 5 minutes or maybe 10 minutes is very, very attractive. So as the market for electric vehicles increases, there will be increasing need. People will want to charge it faster. And of course, consumer electronics would love to have fast charging so that you could charge your phone at a coffee break, you could charge your computer just in 5 minutes. There's a lot of interest in being able to charge consumer devices. But perhaps the one which I think is no one really thinks about too much, but is certainly something for the future, is the Internet of Things. Because in the Internet of Things, we're going to have a wide variety of devices. Some of these are going to be on chip, and that we understand, and that makes sense. And those are going to be almost definitely high power. And the reason they're going to be high power is because these devices, these are sensor devices, they're going to have to communicate to the cloud, and they're going to have to do that with high power communications. It might be for a short period of time, but the point is it does need high power. And of course, that means good energy density. Wearables are definitely going to want to have good energy density so that you can wear it all day long. So the combination of high power and energy and good high power and high energy density is not just for today's applications that we can see, it's for tomorrow's applications as well. So I have very little doubt that this is going to be a terrific area to continue in the future. So what do we know about this? What can we say about the materials that we want, and what kind of characteristics do we want? So in one case, we talked about capacitors, electric double layer capacitors, and this column is going to be all the type of different characteristics. This is the CD plot, and it's a classic box. In batteries, you have redox reactions, and those are peaks that have to do with reduction and oxidation. In between, you have a pseudocapacitor, and these pseudocapacitors are intended to take the best of both worlds. And so let me go through that. So the point is that they're going to undergo redox reactions, and they're going to have two different types. One is going to be at the surface, and if they have redox reactions at the surface, the likelihood is that it's going to be a box. The other possibility is that it's going to be a redox reaction that's going to be more bulk, the way that a battery is. And here you're going to have a region that's probably going to be double layer. And here you're going to have a region that's probably going to be redox active. So that looks like a little bit of both, a little bit of a box, and well, a little bit of a box and a little bit of the redox reactions. The second part is going to be the fact in a galvanostatic experiment, a constant current experiment, you're going to have a constant line. You're going to have a constant dQ/dV. The change in charge with potential is going to be linear, as you see here. And this is what you would expect for surface redox. It's what you would expect for intercalation as well. In the case of batteries, you don't necessarily get that. In the case of batteries, you're going to often have a plateau because of the fact you have a phase transition. And so you have a change in the oxidation state of the material and change in the phase of the material. And this is why you have a plateau. If you get to very small particles, I'll talk about this later, you could start to see capacitive type behavior. And then finally, when we talk about the mechanisms that are going to give you the amount of charge that you want, of, over 500 coulombs per gram, we look at the fact that you're going to want for pseudocapacitive materials, no phase change as you insert lithium at all. Whereas in the case of batteries, you do get a phase change. And of course, in capacitors, it's a surface reaction, you don't see that. So this tells us quite a bit about what we need and tells us quite a bit about where we're going with our materials and what kinds of characteristics we want to have. So from here, let me try to bring it more towards a material standpoint. And let me try to identify the materials, or how to explain how we try to identify these materials. So one of the things we do is voltammetry, because it gives us dynamic information. And in the case of voltammetry, these are CV types of curves. We know that there are, in a way, two different types of characteristics that I just pointed out. In one case, we have classic redox reactions. And in redox reactions, usually it's controlled by the Randall-Sevcik relationship, which tells us about the peak current as a function of the sweep rate. And it tells us that the peak current varies with the sweep rate to the 1/2 power. And that's an example of a diffusion controlled reaction. That's what you have in a battery material. In the case of a capacitor, though, it's different. In the case of a capacitor, the capacitance is equal to the current divided by the sweep rate, which means that the current is going to be proportional to the sweep rate. So in other words, by looking at the current in your device as a function of sweep rate, you look at this power law relationship and you can see there are going to be two different extremes. In one case, if it's diffusion controlled, you're going to get B equal to 0.5. And in the other case, if it's a capacitor type material, then it's going to be B equal to 1. So it's a very simple, straightforward experiment that you can do with your material and immediately tell you about whether you're going to have something that has very good kinetics or something that has kind of slow kinetics. Of course, the good kinetics are going to be when it's linear with the sweep rate. There's another characteristic that we do, and that is to take that information and we say that the current at any potential is going to be the linear combination of two different factors. One is going to be capacitor-like, and the other is going to be diffusion controlled. And so what we're able to do is we are able to take our data that we get in our CV plot as a function of potential, and what we're able to do is to come up with the slope of these curves at different voltages, and as well as the intercept. And what that gives us is the relative amount of the current that is going to be capacitor-like and the relative amount that's going to be diffusion-like. And I give you an example, an old example really, of titanium dioxide, of where we looked at titanium dioxide of different particle sizes. This is 30 nanometers here. These are the redox peaks that you normally see in between a very small capacitive region. As you make the particles smaller and smaller, now you begin to get surface reactions, which is going to be capacitor-like kinetics, and now you begin to get more of a capacitive current. So that literally half of the charge storage is due to capacitive current and not diffusion control. So it gives you an idea, it's qualitative, but it gives you an idea of what characteristic you have of the current, what is carrying the current in the material. So this is kind of a summary of where we are, and kind of, you can sort of sit back and say, okay, so what do we have? So we've been looking at CV plots, current voltage characteristics, and we see that there are two extremes in a way. In one case, we have high capacity, high energy density. That's what we get out of a battery material. And what we know is that in a battery material, when we do our characteristic current, peak current as a function of sweep rate, we will now get a characteristic curve, a log-log plot that tells us that B is equal to 0.5. Lithium iron phosphate is a very good example of a material where the kinetics are diffusion controlled. On the other side, we have a capacitor. And in a capacitor, you now have a box-like characteristic. We know that B should be equal to 1, and here's data that shows that B is equal to 1. This is for a capacitor for carbide-derived carbon, where you get a very nice box-shaped characteristic, and B is equal to 1. So we see that we have these two extremes. But in a sense, we want to have both. We would love to have a material that gives us high capacity, but also high rate. And to do that, we looked at a material, niobium oxide. And with niobium oxide, what we find is that we can almost have the best of both worlds. Now, it's not a beautiful box, but it's not bad either. And the idea now with this box, or with this material, is that here it's kind of box-like, but over here it's going to be more double layer. But more important is the idea that you could charge this material to 75% of theoretical in about a minute. So it has very, very good kinetics. When we do our K1, K2 analysis, we see that B is equal to 1 for almost the entire characteristic. So this kind of formalism that we use seems to work very nicely here with niobium oxide. And so from niobium oxide and other materials, what we've been able to do is to come up with what we call signatures. These are characteristics of high rate redox materials. Let me go through this. And the list of the different characteristics are on the left-hand side. So one aspect is the idea of B equal to 1. This is the surface controlled kinetics that I show over here. And in this case, we have the peak current as a function of sweep rate, and B is equal to 1 up to a very high sweep rate. Then you have some other problems that occur that have to do with resistances that occur in your system. But in any event, over several orders of magnitude, both in current and in sweep rate, you're able to have B equal 1. It's indicative of the fact that the kinetics are surface controlled, which is indicative of the fact that it's capacitor-like. The second characteristic is a linear dq/dV. You look at the potential as a function of capacity, and what you see is very linear characteristic. And of course, this defines a capacitance. So it should be linear because we think that we have a capacitor-like material. The difference, though, is that we have a redox material that's giving us the capacitor behavior. So this is exactly what we want. B is equal to 1, and we're getting redox reactions. Another characteristic is that when you do have peaks in systems, that the offset between the reduction and oxidation peaks are not that large. Part of the reason for this is that in an idealized case, you would want to have adsorption and desorption to be mirror images of each other at exactly the same potential. That doesn't quite happen. There is some offset as you increase the sweep rate, but the point is that this is another characteristic. And then there's the box-like CV. Now, a lot of times you have to use your imagination, but you can see that it's not that bad. Certainly it's not like this, where you have very pronounced redox peaks. It's more box-like, to be sure. And then perhaps the most important part of all this from a physical material standpoint, not from an electrochemistry standpoint, from a material science standpoint, is that you have no phase change in the material. And of course, the reason is because phase changes involve nucleation and growth of the second phase. That takes time, and usually it means it's going to all be diffusion controlled. But if you don't have a phase change, then you have the likelihood that you're not going to have a diffusion controlled process, and instead you're going to wind up with a material that has B equal to 1. And so this is the data for niobium oxide, and you can see that as you insert lithium, the lattice parameters get larger, and then as you take the lithium out, the lattice parameters get smaller. And so it's nice and reversible. There's maybe a 3% change in the volume. So this gives us a lot of metrics for the redox materials. And that's important because now when we start to look at different materials, we want to know, is this going to be a material that's going to be interesting to study? Is this going to be a material that we can possibly make a high rate battery out of it? So with that, let me just review something that's really very important and gets across the idea that not all materials, that you don't have to just stay with intrinsic behavior. So we've gone through some characteristics of pseudocapacitive materials, a box-like characteristic, and this dq/dV being linear. But I also want to emphasize the fact that you can do this by extrinsic behavior. And by that, I mean that what you're able to do is you're able to take a battery material, a bulk material, and now what you're able to do with that bulk material is that you are able to maybe make it into nanoscale, make it mesoporous. You're able to maybe do a delamination, make it a 2D layered material. You're able to do something so that it now begins to look like, it now begins to have pseudocapacitive type properties. And I give an example here of lithium cobalt oxide, where when you make the material just down to 6 nanometers, everything is surface. And when everything is surface, then it becomes pseudocapacitive, and also the kinetics get a lot faster. So it's a very interesting phenomenon that you get. You may not get the same amount of charge that you want, but at least the kinetics are much, much faster. So we're going to talk about a few different types of extrinsic materials. So these are ways that material science people, we're talking about functional materials in this conference. So, how do you take materials and how do you make them so that they can be high rate materials and give you high rate storage? And one way is to make it mesoporous. There's a lot of ways of making mesoporous materials. We like to add some sort of structure directing agent, like a diblock copolymer, and couple that with sol gel process. And then you go through a heat treatment and you make this mesoporous architecture. It's actually an ideal architecture for these types of materials because the pores are open. That allows the electrolyte to diffuse through. So the electrolyte has very good access to the walls of the pores, and the walls of the pores are very thin, maybe 10 nanometers. So the diffusion distances are very short, and these materials look very much pseudocapacitive when you make them. The downside is that you don't get much energy out because these are thin films. But if you need to make a thin film device, this could be a very, very good way to do this. So that's one way of making a high rate material. Another way, as I indicated, is to do exfoliation. And you can exfoliate most materials. I used titanium dioxide nanosheets as an example from several years back, where we exfoliate the titanium dioxide, which are nanoscale. but we exfoliated it in tetrabutyl ammonium hydroxide. And when we made these thin sheets that were maybe 5 nanometers in thickness at most, there were maybe 3 or 4 atomic layers thick, we got characteristics that were very different from the bulk material, from the nanocrystalline material. You could see that there's been a shift in the redox peaks. These redox peaks here are almost absorption and desorption. They're almost mirror images of each other. When we look at the current generation as a function of sweep rate over a couple of orders of magnitude, we see that the B value is equal to 1. The peak separation is very, very small until you get to fairly high rates. And again, when we look at the amount of capacitive material, it's about over 80% capacitive. So this is a very good example of how we're able to take a bulk battery type material. TiO2 is a very nice battery material, a nice anode for lithium. And what we're able to do is to exfoliate it and make it into a pseudocapacitor. Okay, let me move on to the next topic, and the next material, and that's molybdenum dioxide. And in this case, what we're doing is we're creating another material, but now we're suppressing the phase transition. And we suppress the phase transition by making it nanoscale. And I won't go through the details of this, but when we make this, ordinarily the material goes from a monoclinic phase to an orthorhombic phase. But now when you make it nanoscale, it stays in the orthorhombic phase. And now you can generate very high current densities of these materials, very high rate materials, and they retain the high energy density characteristic. And so that's a third way of doing things. Another way of doing things, of creating high rate materials, is by using oxygen deficient materials, by making them defective. And we use the example of molybdenum trioxide. Now, molybdenum trioxide has a very nice structure in the orthorhombic phase. You have a van der Waals gap, but you also have these very nice interlayer structures which allow lithium ions to move through very rapidly. What we did was to make it slightly defective by by losing a small amount of oxygen. We do that through the synthesis technique. And when that occurs, then it turns out that in the 010 direction, you actually open up the lattice parameter. So you make these gaps actually larger and more easy for lithium ions to go through. And so based on this, we began to look at this as a potential pseudocapacitive material, high rate energy storage. And what we find is that when we do make these defective materials, the B value is equal to 1, which is exactly what you want. Another interesting feature is that you suppress a phase transition. This is when the oxidized material has a phase transition in the first couple of cycles. Here, when we go to the reduced material, there is no phase transition in the material at all. And so that part is also very nice. And then also when we go through the galvanostatic characteristics, we can see that it's basically linear behavior. So, and this now again, you're cycling this at 30C, and you're able to get capacities on the order of 100 milliamp hours per gram. And this is over 10,000 cycles. So it's a very, very nice material. What we've done again is we've made it defective. We did that by making this more electronically conducting by taking out oxygen and creating some molybdenum 4+, or rather molybdenum 5+. But the point is that this is a very good way of instilling and changing the characteristics of your battery material and making it into something that gives you high rate. And then the last one I'm going to give an example of is going to be molybdenum disulfide. And with molybdenum disulfide, there's a well-known dichalcogenide. When you make the material, it's in the thermodynamically stable state, in the 2H state, which is a semiconductor. And the structure for the molybdenum is that it's in a trigonal prismatic site. When you put lithium into the material, what happens is that the lithium now will begin to go into the structure, and you will begin to have a phase transition. And you have a phase transition such that the molybdenum is now in an octahedral site. And that's kind of interesting because the 1T phase that you generate is metallic, and that's actually quite good. But the CV characteristic changes dramatically. So instead of having this redox reaction here, over time, as you go through the phase transition, you now go to a box type characteristic, and a better showing down here in the lower left diagram, where we have the characteristic material, and you can see that you have redox peaks superimposed on a box. Over in the upper right-hand corner, this is the evolution of the different structures that form in the material. And then over here, we have the galvanostatic characteristics. And the 2 points to mention here is that you can, when you go from 1C up to 60C, you can see that you really retain a very high capacity. 60C means you're charging and discharging in a minute. And here, this is a characteristic at 10C, and you can see that you retain over 150 milliamp hours per gram over 10,000 cycles, or just about 150 milliamp hours per gram over 10,000 cycles. So it really retained its characteristic, but again, dQ/dV is very straight. So these are all examples of high rate materials and give you an idea about the characteristics that we look for and how we generate them. So now what I want to do is to talk about a practical example, and I'll do that in the next 5 minutes or so. I'll talk about a practical example of how we're going to make a device. We're going to use niobium oxide that I've already mentioned, but what we're going to do is to improve its kinetics by growing the niobium oxide on reduced graphene oxide, on RGO. And we do that through a hydrothermal process. And what you can see is that we make the amorphous phase, and when you put it in the hydrothermal process, you take the graphene oxide reduces to reduced graphene oxide, and also the niobium turns out to be oxidized, the precursor is oxidized, and you form an amorphous niobium oxide. You then go through a post-annealing, and when you post-anneal, you get the orthorhombic phase, which is what we want, on the RGO. And here's an example of where we have a large amount of precursor, very small amount of RGO actually, and you can see how finely divided nanoscale niobium oxide we have on these flakes of RGO. They're very, very well bonded. You get extremely good kinetics off these materials because you have a very good electronic conductivity from the RGO. And this shows us a couple of things. First of all, on the left-hand side, the different X-ray patterns that you get, and the idea that the best materials are not the ones that are most crystalline, but the ones that have a little bit of that are nanoscale. And here from the Shearer formula, we see that this is on the order of 15. The crystallites are about 15 nanometers. This gives us an idea on the right-hand side about the specific capacity that we could get in terms of coulombs per gram. And again, this is extremely good values that we get out of this, and we get these at very high rates, all the way up to a couple of 100 millivolts per second, which is very high rate. So we can see the best materials that we can form. And also we find that this is a very good material, not only from these characteristics, but from the other characteristics that I've introduced. So in other words, we take our material here, the 90% niobium oxide RGO. So there's 10 weight percent RGO in this material. And when we look at the log of the peak currents here as a function of sweep rate, we see that B is equal to 1 over a couple of orders of magnitude, which is good. And if we trace what B is as a function of potential, we see that B is also pretty much equal to 1 throughout this entire potential range. So this tells us that we can nicely operate our niobium RGO electrode, which is going to serve as a negative electrode. We can operate this very, very nicely with very good kinetics. Now, the next part of this, which I'm not going to have a chance to go through, is how do you make this into a high mass loading? And we do this by using holy graphene. And this is a technique, a material that I work with my colleague, Xiaofeng Duan at UCLA. I'm not going to have a chance to talk much about this, but just to mention to you that when we put niobium oxide on the holy graphene, we're able to load it up to over 10 milligrams per square centimeter and still retain its high capacity. And this is at 10C. But I want to move on to the cathode material. And so the cathode material that we've worked with is NCA, in the composition you see over here. And so what happens with this material is that ordinarily, if you make just a rather standard electrode out of it, it tends to have electrolyte, it tends to break down because of various types of electrolyte reactions at the interface. And there's a number of problems that you have with it. And that's kind of traced over here on the bottom part of this curve. But if you coat it with a conducting polymer, and what we used is a thiophene, P3HT, the P3HT has its redox peaks in the same potential region that NCA does. So it matches it extremely well which means that in the regime where NCA is going to give you redox reactions, the thiophene, the polythiophene, is actually giving you more conduction, which is exactly what you want. But it also does one other thing that I'll mention, and that has to do with protecting the surface. So this is just generally the idea about dope P3HT. It's a hexothiophene, and it gives you good conductivity relationships. The other part that I mentioned is that you're able to dope it and undope it at very, very high rates, which is very good. And again, we look at its B value, and the B value is equal to 1 in the potential range where we're going to be operating the material. So it's going to serve as a binder. We're going to use this as a binder, and in this case, we are going to be able to use this material in our battery. So this is just to show very quickly that in the NCA with P3HT, we get much better kinetics, much higher capacity than we do if we use standard PVDF as the binder. But more important is the fact that it turns out that it protects the NCA. And so without going through a lot of detail about this, this is just to show you something about the surface reactions that occur when you have the NCA coated with P3HT versus when you have the NCA coated with PVDF. It turns out that you have many more reactions that have to do with the formation of various oxides and carbonates, and also this lithium fluorophosphate material that you have down here. When you have the NCA that's coated with PVDF, but when you have it coated with P3HT, you limit the amount of reactions that you have. You only have a few products that you have. You eliminate a lot of the disastrous products. So it really serves to protect the surface of the NCA, and that's the reason why the kinetics are so good. And this gives us an idea about the different kinetics. This is the charge-discharge curves in comparing the NCA versus the PVDF. You can see that here that, for example, at 2C, you're at over 150 milliamp hours per gram. And in contrast with PVDF, you're about a little bit more than 100. And then this gives you the waterfall plot. As you increase the C rate, you can see again that at 16C, which is a high rate, you obviously are going to get something well over 110 milliamp hours per gram for the NCA with the P3HT binder versus the NCA with PVDF. So we have a good cathode material, we have a good anode material, now we got to put them together. So here, just to summarize, here's our anode material, and to summarize the niobium on the RGO, we get lithium intercalation, but you can see the B value is equal to 1 throughout throughout the entire potential range you operate this. This is the cathode material that we use, the NCA that's now coated with the P3HT, and we see that it also is giving a very nice characteristic here as well, with a B equal to 1. And then finally, for our battery, we put the full cell together. You can see that over this potential range, we're also able to get B equal to 1, which is exactly what you want. So it's going to be high rate. The problem is that it's only over a limited voltage range. And if we widen the voltage range, then we lose a little bit of rate. But nonetheless, what happens is that we are still able to operate this, not as at higher rate as we would like, but we're still able to operate this with 3-minute charge and discharge. And when we do that, we're able to generate energy densities in excess of 100 watt hours per kilogram. And this is now cycling at 16C for 500 cycles. And you're able to still retain 100 watt hours per kilogram at this high rate, which is actually right around 5,000 watts per kilogram. So you have, in many ways, the power of a capacitor and the energy density of a battery material. So let me summarize then. I've come to the end of the talk. And so what I've tried to do then is to show you about how we identify high rate redox materials. We identify certain signatures so that you can identify which are the materials that you really want to work with. And this is some of the characteristics that I mentioned. DQDV is straight, there's no phase change, and also you like to have sweeps where B is equal to 1. And then there's a number of other features that I mentioned with regard to significant materials related issues, the modifications of niobium oxide and NCA that enable you to have good kinetics. And then the idea of the fact that the NCA with the binder prevents any kind of electrolyte breakdown. And then finally, that we've demonstrated prototype devices that have 110 watt hours per kilogram at 5 kilowatts per kilogram. As I mentioned before, this is really battery type characteristics of energy density, and this is at, at power densities that you have for capacitors. So with that, let me thank my colleagues who worked with me on this project, Professor Sarah Tolbert, and then a number of graduate students who have gone on to very nice careers and postdocs as well. And with that, let me thank you. Let me again thank the organizers, and I'm very I'll be very happy to answer any questions. Thank you.
Thank you, Professor. Now, paper is open to questions and comments. Is there any questions? Professor Sakir, Imran, can you hear me?
Yeah, can you hear me?
Yes.
Yeah,
yes.
Brother, thanks a lot for your nice talk. I just had a quick question. As you mentioned in your talk, like for industrial application, we have to look for the mass loading for the anode or active material. So if we increase the mass loading of the active material, how does it affect the kinetics of the electrode, and how we can control that one?
So it very much depends on the conductive support. I didn't have time to go into that, but we find that holy graphene is extremely good. And with that, we're able to get loadings of no problem of 10 milligrams per square centimeter. So that part is extremely good. So it really depends on being able to come up with a very good conductive support. And at the same time, you don't want to have too much of it, because the conductive support does not give you any capacity. But that's an important issue, and I can assure you that I have colleagues who are working on this, and they've been very successful in being able to generate very good devices, really, 1 amp hour devices with these materials.
Thank you. Thank
you. Okay, Professor Kang.
Hi, it was very nice overview of high rate batteries. I'm just wondering if there's any great prospect of these MXenes, which is one of the emerging materials. So I just wanna hear your comments on MXenes in this research area.
Right. Well, the capacity for lithium by the MXenes is not that high. So the capacity is not that high, so it's kind of limited in that sense. The capacity that you saw for the niobium oxide, for example, was much higher than you would get. So you would lose capacity. So it's going to be a bit. So MXenes are going to be a bit limiting. MXenes have very, very good rates, and so they would be able to go to other types of applications that I mentioned before. In particular, I think that micro devices would be an extremely good area for MXenes.
Thank you, Professor. Is there any other question? Okay, if there is no more question, we should move on to the next presentation. Let's thank speaker again. Thank you, Professor. Okay, let me call the last speaker in this session, Professor Jae-Eun Jang from DGIST. His presentation is on the recent work on the psychological tactile sensor employing piezoelectric material. Professor Jang, give a presentation when you're ready.
Thank you, Mr. Chairman, for the kind introduction, and I would like thanks to the organizing committee giving the chance for this invited talk. And hello, everyone. I'm Jae-Eun Jang from Daegu Gyeongbuk Institute of Science and Technology. Today, I'd like talking about the psychological tactile sensor employing piezoelectric materials. As you know, human has the 5 sensory systems. So eye, ear, tongue, and then finger or skin and tactile system and nose. And then many science or engineers want to mimic these 5 human sensory system. And the reason is actually that we succeed to mimic eye and ear. Actually, the ear make the recorder, and then eye mimic devices, camera, and then reverse engineering, there is actuator also produce the audio and television. As you know, this 4 invention is the most important invention in last 100 decades, and then they made tremendous impact to the human life. So we think if we succeed to mimic another remain ones, we also give high impact to our human lives. However, when you look at the history of the ear of eye, we know why ear and eye can mimic first. The reason is there for the recorder case. Anyway, the input parameter is just 1 frequency, and eye case input parameter is 3 RGB light. So actually that means if we have the smaller input parameter for the scientist engineer can develop easily. However, unfortunately, for example, nose, in that case, there are the human has around 100 receptor, and for dog generally has 300 receptor. That means we should develop the 100 different sensor or 300 different sensor with high selectivity and high sensitivity, and also we need the high integration skill. So it is the hard for our engineer. So we believe the next one is the tongue or the finger, because the tongue case, actually the input parameter is around 5 to 6, and then finger is also similar. However, considering the application field, tongue is limited, so we want to develop the artificial finger system. So when you look at the developed history of the finger system, actually the tactile system have been developed well in robot field, especially for the Android robot or something like that. And that field, they want to hold some objects using this kind of artificial tactile system. However, unfortunately, this kind of development does not induce the high impact for our life. Ironically, actually, the most simplest tactile system, touch sensor, produced the high impact. Actually, this tactile sensor embedded to the smartphone, and then they give the high impact. The reason is not just come from the hardware issue. Actually, it also come from the software issue. So the reason is that this tactile touch system produce new user interface, and then they produce high impact for our life. So considering this point, actually we want to mimic whole tactile system. That means general research case, most of the tactile sensor focused on this kind of the physical mimic ones. So most of the research want the high sensitivity pressure sensor or temperature sensor or vibration sensor. However, if you consider human, actually the human make some finger motion using this kind of the physical input detection. However, the other point, we also produce some tactile feeling from the brain signal process. So our research motivation leads to this kind of the psychological tactile feeling. So we want to produce the artificial pain, or we want to produce artificial smooth or low feeling using this tactile system. So we want to mimic brain signal process as well as the development of this kind of the tactile sensor. So you can choose the various kind of the mechanism for the tactile sensor. So resistive or capacitive type is well known. So we use this sensor system for the ATM machine or your mobile phone. And then optical or ultrasonic, magnetic, and piezoelectric type is also developed for the tactile system. So to choose appropriate one, we have the three important criteria for the mechanism selection. So for the tactile system, so most of the important two parameters is the pressure detection and temperature, and then also to produce the very kind of the tactile feeling, multi-touch is also important factors for the mimic system. And then using this kind of the three criteria, finally we choose the piezoelectric time material. One reason is actually that this kind of piezoelectric time material can detect pressure, temperature together, because we can use the pyroelectric effect as well. And then also it is good for sensor because they produce power without the consumption of the electrical power. That is one of the merits. And then this is the another reason why we choose the piezoelectrical material for the tactile sensor. So physiological analysis of the human skin shows the piezoelectric-like or pyroelectric-like behavior. So they produce spike-type signal from the mechanoreceptor or thermoreceptor inside the human. And then, so we believe the piezoelectric is the quite good candidate for the tactile system. So we start study about the PVDF material. The reason you know well, actually it has the many advantages. Actually it's quite flexible, and then fabrication process is quite easy, and then it produces good power when you touch them material. And then this is the well-known piezoelectric material, and then it also produces the pyroelectric effect. So that means we can detect pressure and temperature together using this kind of the PVDF material. So this is sensor result. So this is the responsibility for the pulse, and then this is the responsibility for the temperature, and then it has the good linear relationship, and then sensitivity is quite good. But there are some problem in there. There are two results, and then one result come from this kind of the pressure state, and then one result come from the hot object. And then when you look at this signal, you don't distinguish well which one come from pressure and then which one come from the heat object, because both of them produce just this kind of the spike type signals. For the energy harvesting, it doesn't matter what is the energy source to produce this kind of signal, but this is a sensor. So sometimes we can produce the prick sensation, and sometimes we can produce the hot pain. And then in that case, the energy source is different. So distinguish of the energy source is quite important. So that is the problem why we can't use this PVDF for our sensor system. Of course, when you look at the piezoelectric signal and pyroelectric signal, actually the level and shape is a little bit different. So if we use the complicate the signal process, you can distinguish this signal as well. However, when you consider reliability or power consumption of the signal process, we think this is the no good approach for our idea. So we try to change material to the zinc oxide nanowire. For the zinc oxide nanowire case, actually the one of the unique characteristic of zinc oxide nanowire, that also produce the piezoelectric effect. However, that material is semiconductor material, not insulator. General piezoelectric material is insulator. However, zinc oxide case, uniquely it shows the semiconductor characteristic. So that means actually we also can generate the Zeebeck effect using this kind of the zinc oxide nanowire. So this kind of the different Zeebeck mechanism from the piezoelectrical effect, we can distinguish the energy source using just one material, we think. So to produce the Zeebeck effect anyway, precarrier is quite important. So to produce the good Zeebeck effect, we need the certain amount of the precarrier. However, when you grow the zinc oxide, normally we try to the annealing process to reduce oxide defect to get high piezoelectrical effect. However, in our research, we don't try any post annealing, and then we remain the oxide vacancy. And then we use the gold electrode, and then during growth process also gold impurity diffused to the zinc oxide nanowire. So we can produce enough precarrier to induce the Zeebeck effect. So this is the result. So when you touch the hot object of the top side of the zinc oxide, actually they can produce two mechanisms. One is the pyroelectric effect, so volume expansion, and the other one is the Zeebeck effect. So when you touch the top object, actually the pyro effect and then Zeebeck effect, the direction is different. Direction is same, so we can get this kind of the finite signals. However, when you touch the hot object to the bottom of the zinc oxide, actually Zeebeck effect current and then pyroelectric current is the opposite direction. So finally, we cannot detect any signal. So we can prove this zinc oxide produced the Zeebeck current well. So we can use this zinc oxide for the temperature detection as well as pressure detection. This is the result. So when you touch the zinc oxide, they produce general spike type, the piezoelectrical signal. However, when you touch the hot object to the zinc oxide, in that case, they produce this kind of the DC-like signals. Actually, it comes from the Zeebeck effect. So we clearly distinguish when you look at the signal, what is your energy source produced this kind of the signal. So we can detect pressure and temperature together, and then we also distinguish both of them. However, I already mentioned, so we want to produce the precarrier inside of the zinc oxide to make the Zeebeck effect. So there is a log point for the piezoelectric behavior. So to compensate this kind of the poor piezoelectric powers, we want change some structural point to compensate the kind of the demerit. So left side shows the zinc oxide nanowire grown on one single electrode. This is the one cell structure. However, we change this kind of the patterned design. So the reason is that if we can change the population of zinc oxide nanowire, actually even you apply the same force, actually the pressure level is increased. So you can produce much higher signal than high population structure. So we make the small size pattern on one electrode. And so we can produce the lots of the edge area, and then edge area also has some merits. So when you look at this edge side, nanowire grown tilted a little bit. So if you apply the normal force, this tilted nanowire bending, then compression state, and then they produce much higher piezoelectric signal than just vertically grown the zinc oxide nanowire. So we can compensate the defect effect on zinc oxide nanowire. However, there is some issues. So we still have issues. So if we use this kind of the zinc oxide nanowire, we can detect well temperature and pressure together, but we cannot solve the reliability or uniformity between the growing loss. So that is the issue. So our third approach is the separation. So this is the general engineering concept. So we made the two sensor, not just a single sensor, to detect the temperature and pressure. So we made the resistive sensor to detect the temperature, and then we also made the PVDF array sensor to detect the pressure. So we can detect pressure and temperature together. To minimize the fabrication process issue, we choose a single resist type sensor. However, this single resist type sensor design also make some problem. So when you look at the general thermometer, most of the case, the sensor size is smaller than detecting material or object. So recently we detect the body temperature quite a lot. In that case, so thermocouple sensor is smaller than our body, so there is no problem. However, for our application, sometimes quite small object than sensor dimension, we have lots of time that kind of the example. For example, hot needle can detect our sample. And when you look at in here, so if the object size is smaller than sensor, in that case, make problem. So actually the results depend on the size. So we should solve this point. So to solve this kind of point, we use the under pressure sensor. So when you try to detect the pressure level under the resistive sensor, we assume the touch object size using this kind of sensor layer. So if you know the object size, you can modify the resistive change result, and then you can get exact temperature values. And the other signal process scale is the we measure the resistive change on this kind of the slope region, not saturated state. The reason is that if we use this kind of the slope region, then the saturation case, we can minimize detection time. So in this case, detection time is just 100 milliseconds. So when you think about the general thermocouple or thermometer case, you need 1 or 2 seconds to get the temperature region, but it is no good to produce the hot pane. Actually, when you touch the hot object, you pane produce exact suddenly, so quite a short time. So we use this kind of the slope analysis technology to get the temperature level. And this kind of slope analysis also gives some merits. So when you touch the small object to the sensor, actually the X and when you look at X and Y, for the X region connected to the large size the contact pad, so thermal conductivity is different from the Y position. So in this case, when you look at the saturation value, even same temperature and same size material, but result is different. However, when you look at the slope analysis, actually the each shows almost similar slope value. So we can get the same temperature in these three different cases. So we use slope detection process to detect the temperature. To get the exact dimension, touching object dimension, so we try to analysis pressure level and then pressure area. So sometimes maybe actually this under pressure sensor array resolution is not higher than the general object. So it means object can touch the sensor partially. So however, this kind of the partial touch state can calculate from the generating voltage, and then this generating voltage is well correspond to the total touching area. So using this kind of the signal process, even the sensor resolution is not higher than sensor object, we can assume the touching object dimension quite exactly. So this is the result, and then we touch the various points using 3 millimeter diameter, 2 millimeter diameter cylindrical object, and 4 and 7, and then when you touch various points, and then finally we get quite good result, and then we can sense temperature and pressure together. So this is the diagram how you can produce artificial pain. So if the material touch the system, first one, they evaluated the dimensional point, and then if we know, for example, the object is too sharp, in that case we check the threshold level, that is the pressure level, and then pressure level is higher than the threshold, we can produce the prick sensation. And sometimes maybe material is not sharp, however, it's hot. In that case, we also check the temperature, and then finally we can produce the hot warning. So this is the signal process, and then, oh, sorry. So this sensor prick the sharp object, they feel the prick pain, so they return back to the original position. And then sometimes they touch the hot object, they feel the hot pain, so they also return back to the original position. So we can use our system for this kind of the application. And the other part is we also try to produce artificial smooth or rough feeling. So due to the time limit, I briefly present this part. So we also produce another psychological tactile feeling, so rough or smooth. So for the human to produce normally we produce the rough or smooth feeling when we touch a certain texture. So when you consider the mechanism, human thinking, actually there are lots of the parameters to produce rough or smooth feeling. So in here, most of important parameter is surface shape. So surface topography is important, and hardness is also important. And then temperature or vibration is quite the important parameter to make this kind of rough or the smooth feeling. But unfortunately, there are some problems. So even brain scientists, they don't know well how we can produce rough or smooth feeling. So they don't know mechanism well. So that point is the challenging issue for the general device engineer. So we should know the mechanism to mimic certain system. So so far we can mimic this kind of the tactile feeling. However, recently, actually the machine learning studied quite well, and then it developed. So if we use the machine learning, actually that mechanism is not the same of the brain signal processing, but we can mimic that function. So we believe this kind of the mimic profile can produce artificial rough and smooth feeling. So to detect the surface topography, actually that is quite important to produce the rough or smooth feeling. But the general case, many of the approaches like this one. So many people want to make the array structure to detect the surface topography. However, for example, there is a ring, and when you put the ring inside in there, actually the maybe final result is not ring, it's a square. So that means array resolution should be higher than material, but it means in that case, we need quite high resolution tactile sensor. So maybe it's a challenging point. So to solve this point, we mimic human motion. So for the human case, when you produce the rough or the smooth feeling from the texture, first you touch the texture, and then you slide on the texture, and then finally you got that feeling. So when you try it, actually the sliding motion produce more clear sensation than touch one. So we mimic this one. So we want analysis piezoelectric signal when we slide object under our sensor system. But there is some issues. So if we use the resistive or capacitive sensor, actually the result profile is quite similar to the your touching object, the surface topography. However, piezoelectric sensor case, they just show this kind of the spike type result. So this means we need more signal process to get the surface topography. So we try to get the surface topography from this kind of the piezoelectrical signal. So this is our system. So we made this kind of sensor system, and then this sensor system touch an object and then slide on the texture, and then finally get the surface topography or the hardness. So to get the surface topography, so sliding speed is also important. So if you don't know the sliding speed, actually this is the time domain signal. So this is the piezoelectric time domain signal. So we just know the time domain one. So we should change this time domain to the centimeter or millimeter scales. In the case, we should know the velocity of the sliding. General case, for the AFM case, we know the speed. Actually, that system has a speedometer, or they fix the speed. However, in this system case, we made this kind of the array sensor. So if you use the two adjust the sensor, you simply get the speed. So this is the how you can get this kind of speed. So actually, the one object touches these two sensors. So same object touches these two sensors, so they produce same signal, but it just has the time difference. So if you know the design, it means the spacing between C and B and C cells. So finally, you get the sliding speed easily. So actually, even the sliding speed is random. In that case, we also can get easily. So from this kind of results, we can calculate where the sliding speed and then size of the touching object. So we can calculate surface topography easily. So in this case, actually we have the many shape in there, and then finally we get the exactly shape from this kind of the sliding motion and analysis of the piezoelectrical signal. So when you look at in here, so actually we get quite well two-dimensional information, but problem is the depth information. When you look at the human finger, actually the human finger is quite flexible. However, even we developed a good flexible technology, actually that is based on the thin film structure. So if the flexible change is not similar to the human, so we should solve this issue. So we use the soft material, and then we try to get the results. However, the results actually it gives the poor depth information than the human. So we try to make this kind of the pin module structure. So even this is even not flexible, but this pin module can work well for the quite this kind of the rough structure. And then from this kind of the rough structure, we get the good depth information with high two-dimensional results. So if you get the good surface topography and hardness or temperature, finally we try to the machine learning. So actually we want to make some tactile avatar system. That means this system mimic human's preference. Actually, maybe human has the smooth, soft, or the rough feeling when you touch the texture. However, problem is actually it depends on the personal preference. So how you can mimic that kind of one? So we use the machine learning system, and then we give the weight when we decide a certain material is soft and then certain material is rough. So we trained around 50 materials after we get a certain master's decision, and then after filling, after the running process, we can make tactile avatar system. So this is the final system. So previously I already shown. So they peel the paint from the sharp or the hard objects. So actually this video has sound, but there is no sound due to the systemic problem. Anyway, when they don't peel the paint, they touch the object, and then they make the sliding motion, and then finally they produce, oh, this texture is smooth, and oh, this texture is the rough, and then that decision is quite correspond with the master's decision. And then even unknown material, that means the not trained material. So that means even we don't know, some master has the certain the final feeling. In that case, the correlation is higher than the 90%. So we think this is quite a good system to produce artificial tactile sensing. So we believe this system for the various kind of the field, and then, for example, this system can apply to the Android robot. In that case, they can peel paint, so they can protect the body from the harsh environment. Or sometimes maybe this system can apply to the internet market, and then we can peel the text filling using your avatar system. Also, we can apply the human interfacial system using this kind of one. So I'd like to thank to the Yeri and Mingyong and Kyunghwa, Kwansik and Mins for these results. Thank you for your attention.
Thank you, Professor Zhang, for the nice presentation, and it's very crucial for the future human society. Now, paper is open to questions or comments. Any questions? Hey, Professor.
Thanks for your nice presentation. Would you explain a little more about the slope analysis? Yeah, yes. Yeah. Yeah, how can you determine the slope in your sensors?
Actually, this is the low result. So we get this kind of the resistance change. So even object does not touch the sensor. Actually, the object just position near the sensor. Actually, the heat transfer to our sensor. So they start this resistance change. So we try to get the first derivation value, then this kind of the starting point, because this highest the derivation value means object touch the sensor, and then this is starting point, and then from this starting point, we give the 100 millisecond interval, and then we get the second point, and then finally we get slope.
So you mean in your sensor, you measure the resistance per every 0.01 seconds. So you need quite fast and the expensive analysis tools. I mean,
Actually, for the pressure sensor, anyway, there are some array in there, and then we need a high response time to produce the certain filling. So maybe we need the budget to make the total system, but actually we think about some IC technology. Actually, we embedded some specific IC technology or something like that. I think the final system price is not high.
Okay, thank you.
Okay, any other question? Then may I ask a quick question? Professor Zhang, you talk about the tactile sensor, which means people may touch your sensor or wear it, right? So that means that people are very keen to the safety issues. So is there any safety issues like electric shock or chemical or biological safety issues?
In my case, the general application is not huge. The general application is the robot or certain electrical device. Maybe we apply my system to the smartphone. In this case, maybe you sorry, but it's quite similar to the general touch sensor in smartphone, so we can solve the kind of the safety issue easily.
Thank you for your answers. If there is no more questions, then let's thank the speaker again. Thank you, Professor Zhang. Okay, now all the scheduled presentation are done. Thank you for your participation in this session. And there is a best poster presentation ceremony here. Please stay and attend the ceremony. The award will be given by the Professor Dae-Jung Kang, the conference chair. These all poster presentations are presented yesterday. So third best poster award winner, Seung-Woon Baek from Cha University, Sung-Baek Yang, Gyeongbuk National University, and Junwon Bae, Dongdeok Women's University. The award winner, please come to front side. Second. Seung-Woon Baek from Cha University, Sung-Baek Yang from Gyeongbuk National University, Junwon Bae from Dongdeok Women's University. Unfortunately, this poster award winner not attend these ceremony sessions, so we are going to post all certificate and additional prize to them. Okay. Second best poster award winner, Shaka Plak from Inje University. Okay. Seung-Woon Bae from Cha University. maybe there's a technical issues. So, okay. The certificate and additional prize will be given by Professor Kang. And third best poster award winner, Junwon Bae from Dongdeok Women's University. Okay, second best poster award winner, Shaka Palak from Inje University. A certificate and prize, additional prize are given. Dongjin-nam, Chungnam National University. Dongjin-nam? Okay. We will deliver the certificate and additional prize by post. Okay. The best poster award winner, Sunjin Lee from Korea National University of Transportation. Congratulations. Okay, all morning session is closed, finished, and after the lunch break, we are going to start the oral session here. It's about the advances in polymer and ceramics, low dimensional and nano and 2D materials. It will be start 1:30. Thank you.
ceramics, low-dimensional, and nano and 2D materials. First presenter is from Sungkyunkwan University, is Moon Byung-seok. The title is Green Conversion Enhancement Achieved by the Laser-Induced Transformations from the Beta Nano NaYF4 to iridium oxide.
Good afternoon, everyone. My name is Byung-seok Moon. I'm a postdoc in Sungkyunkwan University. Today, what I'm going to talk about is green upconversion enhancement achieved by laser-induced transformation from beta sodium ethyl fluoride to yttria. Upconversion luminescence is a unique optical process that converts low-energy photons into a higher-energy photon, unlike conventional luminescence that convert high-energy photon into lower-energy photon. Upconversion luminescence is facilitated by lanthanide trivalent ions because it has ladder-like energy structures and long-lived intermediate states to realize easy multiphoton absorption. So when we illuminate near-infrared light, NIR light, on upconversion materials, we can see visible light from upconversion materials as a result of upconversion. Upconversion has created many fascinating applications in diverse research fields because of its unique use of NIR as a light source. For example, solar energy harvesting, security patterns, latent fingerprinting for zero background forensics, and because NIR can penetrate tissue deeper than visible light, upconversion materials has demonstrated deep tissue optogenetics. This is important because in conventional optogenetics, we have to open skulls or tissues to realize optogenetic effects, but using upconversion materials, we don't have to open skulls or tissues. In upconversion, there are two popular host materials. First one is sodium ethyl fluoride, and second one is yttria. For brightness, sodium ethyl fluoride is the best choice because its low local symmetry can facilitate the breakdown of Laporte acceleration rule, that is the main restriction of upconversion efficiency. However, peak sharpness and thermal stability of sodium ethyl fluoride is inferior to yttria. So silicon-based optoelectronics, which is the potential application of upconversion, which requires high temperature annealing process above 800 degrees Celsius, sodium ethyl fluoride is unsuitable for these applications. Therefore, if we can make bright yttria-based upconversion materials, it would be great for next generation silicon-based optoelectronics. Before we see short video of experiments, I will explain the detail of experimental method. We prepared sodium ethyl fluoride microplate, which is singly doped with erbium 0.5% to realize green upconversion emission. The microplate was placed on nickel substrate and irradiated by highly focused laser beam. So, sorry. When we irradiate moderate power, we can see typical emission spectrum When we irradiate moderate pump power, we can see the typical spectrum of sodium lithium fluoride. However, when we increase pump power, the former peak has been increased greatly. It indicates that the local temperature of the microplate has been increased a lot. And because of the local temperature increase, after a few seconds, the emission was quenched to zero and rose back with significant accommodation enhancement. Interesting observation is that the emission was changed from sodium lithium fluoride to yttria. To reveal the origin of accommodation enhancement, we check the cross-section of the microplate using FIB techniques. As you can see, there are many nanoscale grains in the microplate, which was conformed with SAED patterns. In SAED patterns, the scattered bright spots indicates that there are many grains with different directions in the tiny diffraction spot, which is 500 nanometer in diameter. And also the composition was changed from sodium lithium fluoride to yttria along the vertical directions. From these results, we conclude that the microplate was changed from sodium lithium fluoride to yttria by the incorporation of oxygen in air with extraction of sodium and fluorine content to fabricate disordered crystalline yttria. Next, we investigated the atomic arrangement in the microplate using high resolution TM images. As you can see in the pictures, the atoms were displaced from its periodic and ordered sites. This kind of atomic disarrangement is important because it can provide non-central symmetric crystal fields around lanthanide ions to induce parity mixing between 4F and 5D states. And this is the main fundamental physics in the breakdown of Laporte selection rule, which restrict the accommodant efficiency. So we can say that the accommodant efficiency has been increased by the non-central symmetry crystal field around lanthanide ions in the microplate. And the breakdown of Laporte selection rule can be supported by greatly shortened decay time. Another interesting observation is the power dependence of disordered crystalline yttria. The steep slope and no saturation in power dependence compared with moderate slope and easy saturation of sodium lithium fluoride. That is important because we can further enhance accommodant efficiency when we pump the microplate with higher power than I did. These are my conclusion and further work. Bright green accommodant has been achieved by laser-induced rapid transformation of beta sodium lithium fluoride, and disordered crystalline yttria reinforces non-central symmetric crystal field for accommodant enhancement. And also, I will analyze the steep slope of disordered crystalline yttria by using greatly shortened decay time. And the rapid transformation technique will be applied for energy transfer accommodant systems, which utilize ytterbium as a NIR sensitizers, because we only tried singly doped erbium system to realize green accommodant emission, but ETU system is more efficient than singly doped system. So when we apply our rapid transformation technique on ETU system, then we can expect more further enhancement of accommodant efficiency. This is my presentation, and thank you for listening. Any questions?
question, please? Okay, I have one question. You mentioned about the temperature is quite high about that. So is there any chance about the reduce the temperature to make lasers?
Temperature reduction? Actually, thank you for your question. Actually, we can control the local temperature by adjusting the laser power. And in my experiments, I did many. I tried many pump powers, but using 3 million watt per centimeter square is the best for the reaction, and lower pump power cannot induce the transformation. So I think we have to increase power to increase higher temperature, not to reduce the temperature. Thank you.
Thank you very much. Next presenter is from University of Seoul. Presenter Yong-Min Kim, and the title is Non-Volatile Ultra Stretch Ionic Sensory Platform for Next Generation Wearable Electronics.
Good afternoon, everyone. I'm Yong-Min Kim from University of Seoul under the guidance of Professor Hong Chul-man. It's a great honor to introduce my research in this seminar. I appreciate the committee and the chair. Today, my topic is non-volatile, ultra-stretchable, and ionic sensory platforms for next-generation wearable electronics. I'd like to start by looking at this exponential growth of wearable electronics, referred to as E-skin. E-skins are the flexible, stretchable, and self-healing electronic materials that can mimic the functionalities of human or animal skin. The broad class of materials containing sensing abilities that are able to introduce to respond to environmental factors such as changes in temperature, humidity, and pressure. Therefore, there have been many efforts to develop the high-sensitive strength sensor, such as carbon material-based textile, or liquid metal, or encapsulating ion liquid into the elastomer. And moreover, the hydrogel and ion gels are the growing fascinating materials that are used to strain sensor due to their highly flexibility and highly transparency. However, there are also many defects to develop the strain sensor because the complicated fabrication process and the agglomeration problems of conductors are problems due to their discontinuity of the reversibility and the long-term durability. And moreover, the hydrogel-based strain sensor have a serious problems to develop to maintain the sensitivity because the drying issues of water. Therefore, they need an additional process such as encapsulation process, or they need to add some humectants to prevent the water drying. And moreover, the conductor-based elastomer strain sensor have a limit range to endure the applied strain. Therefore, in this study, we focused on the ion gel system. The ion gel consist of copolymer and ion liquid. We approached the designing process of molecular structure of copolymer because the gel performance, such as characterizations of mechanical strengths, are strongly dependent on the copolymer chelators. So we made the PMMA random PBA copolymer by simply using the Raft polymerization method. By simply mixing the copolymer and ion liquid, the physically cross-linked ion gel are produced. And this PMMA random PBA copolymer shows highly stretchability, more than 850%. To figure out this highly good stretchability, we also synthesized PMMA homopolymer and PMA homopolymer, which has high Grass transit temperature and low Grass transit temperature than PMMA random PBA copolymer. Some studies argued that the low Grass transit temperature is crucial factor for chain flexibility. Therefore, we simply tested the 3 types of ion gels. Look at this DSC data, and strain stress curve shows that the low Grass transit temperature is significantly affect the chain flexibility. However, not significantly affect the ultra stretchability. Yeah. Therefore, we look at these microscopic images. Look at these images shows that the PMMA homopolymer ion gel and PMMA random PBA copolymer-based ion gel shows good mixed system, but not PBA-based ion gel. And moreover, the small angle X-ray scattering data shows that we extract the agglomeration size of this data by using the simple linear Pollard regime. These two data shows that the PMMA random PBA-based ion gel has a larger agglomeration than PMMA homopolymer-based ion gel. Putting it all together, the PBA domain is not dissolved in ionic liquids. Therefore, we conclude that the low Grass transit temperature and ionic insoluble domain are crucial factor for chain flexibility. To verify our assumption, we also synthesized PMMA random PS copolymer, which has ion liquid insoluble domain as PS styrene domain, and if this is higher Grass transit temperature than PBA domain. Therefore, in these two data also shows that the PMMA random PS copolymer based ion gel could be stretched more than 500%. Therefore, we can conclude that the low Grass transit temperature of ion liquid insoluble domain are main factor for stretchability. Therefore, we finally conclude that the copolymerization of ion liquid insoluble domain, which has low Grass transit temperature, is the main factor for chain flexibility and showing ultra stretchability. And furthermore, we can optimize the copolymer gelator by control the molar ratio of copolymer. Look at this rheological data. When the PMMA domain are higher than PBA domain, the G prime is reversed by G2 prime in low frequency. And moreover, if the PMMA domain are higher than PBA domain, the G prime is also reversed by G2 prime in high frequency. Therefore, we adjust the optimized molar ratio as 88% of PMMA random PBA copolymer, which shows always G prime is higher than G2 prime in all frequency. And finally, the strain and stress curves are maintained like this. And moreover, the ionic liquid concentrations are important factors for evaluating the gel performance. In literature, the two main characterizations of mechanical strength and ionic conductivity is in trade-off relationship. Therefore, we precisely control the ion liquid concentration of the polymer gelator. And look at this Bode plot and strain stress curves. We precisely control the ionic liquids and optimize the best concentration as 4 to 6 molar ratio. And this shows highly stretchable and good ionic conductivity. And we further examine the cyclic stretching releasing test. And the mechanical reversibility was simply earned by the recovery ratio and residual strain. And this PMMA random PBA based ion gel also maintained the initial initial strain stress curve more than 500 cycles. And after 500 cycles, the recovery ratio was almost remained in 100%, 96.1%. And more interestingly, the ion gels are themselves ionic conductor. Therefore, the PMMA random PBA copolymer-based ion gel could be used as wireless strain sensor by simply connecting the gel and to the digital multimeter. Look at this image. The brightness of the emitting lights are gradually decreased when the gel are stretched. This also shows that due to the increasing resistance, the emitting lights are gradually decreased. So we can check the resistance change by applying the barrier strain. And this gel performed very good gauge factor 2.73, which is higher gauge factor compared with previously studied strain sensor, and it can remain the initial amplitude after 13,000 cycles and stable in 10 days without any encapsulation process due to the high vapor pressure of ion liquid. And finally, for the visual demonstration, we employed the gel as the skin type wearable sensor. By simply attached to the human body parts, and we call the gel as ionoskin. The ionoskins can attach for human representative body parts such as finger, elbow, knee, and ankle, and it can detect the various human motion such as finger movements or elbow movements, and jumping motion, and even the human working movements speed. This all data shows that the tremendous potential for application in future robot or human skin. Therefore, in this study, we finally conclude that the rational design of new random copolymers are good point for evaluation of the stretchable ionic sensory system, and we analyzed various gel characterizations and demonstrated as the ionoskin and attached to the human body parts, and we can detect the various motion. And finally, we conclude that this could be used as the potential robotics wearable real-time human skin. And this is the end of my presentation. Thank you for listening, and we are open to any question.
Thank you very much for your presentations, and any questions? Okay, I will have one more question. You mentioned about the non-volatile.
Yes.
So non-volatile means that some kinds of memory.
Yes.
So in your device, what's the meaning about the non-volatile?
I already thank you for your good question, and that is very important factors for evaluating the gel strain sensor or any other robotic skins. I mentioned above that the hydrogels are non-volatile. Hydrogels are volatile because the drying issues of water. But however, in my system, the ion gel, due to the non-volatile properties of ion liquid, due to the high vapor pressure of ion liquid, we can use this without any encapsulation process and detect any, and simply putting it ambient state without any encapsulation process, we can detect every single movement more than 10 days. So yeah, I think the non-volatile properties are very important factors for developing the future wearable electronics. Thank you.
Any questions? Okay, thank you for your presentation.
Thank you.
We can move third presentation from Yonsei University, Kajabi Radeshi, and photografting coating of p-isoline onto the polypropylene surface as a free radicals communist backing.
I'm Kambis Sadeghi, student from the Yonsei University in the packaging department. Today I'm about to talk about our recent work. This is a new version of the non-migratory active packaging in the contribution. We will talk about the migratory and non-migratory. The perception about the packaging is mostly about the primary properties, like some kind of protection or some kind of structure for deliver the products. But in the new generation of the packaging, we have a active packaging. Active packaging definition is intentionally addition of some active materials. That active materials can gives some active function like antimicrobial, antioxidant, or some kind of scavenging for the packaging. The conventional packaging materials in the market, they are just it's a type of the mechanical or barrier materials, but those packaging systems in the market, they cannot protect about the shelf life. But the active packaging can enhance and extend the shelf life of the products. So, the recent work in the active packaging is mostly about a migratory packaging. It means when we look at the biomedical or the food items, they have a synthetic antioxidant, and sometimes they use some bio-based or originally from bio resources used as an antioxidant, but all of them needs to migrate or need to be dissolved in the product. So they have a diverse of the problems. The most important one is that when we use when we take for a long terms of the usage of some kind of the synthetic materials or some kind of the bio-based materials, they have some health challenge for human. And even they don't have health challenge, but when they migrate to the products, they will change the sensory products. And in the way these days they are using the active packaging, they incorporate the active materials into the polymer or the packaging. So those materials can change the primary performance of the packaging, like a barrier or mechanical or barrier properties. So they interfere in the packaging performance. In our work, we was intended to develop a non-migratory antioxidant packaging. The antioxidant needs to do three important works or actions. The first one is they need to scavenge free radicals in the system, chelate the transition metals, and quench those reactive species free radicals or peroxidants. In this work, we use the para-anisidine. Para-anisidine is a kind of the conducting polymer. In the engineer, they use as a conducting polymer. But in here, we were intended to use these materials as an antioxidant. The technology we use for this work was about the photografting mechanism. We grafted photochemically monomer on the surface of the film. Our film is polypropylene. We exposed our polymer to this coating solution. Coating solution is containing some kind of the monomer in the presence of the photoinitiator. Mostly for the surface photografting, benzophenone is a common
go on. Yeah.
We UV irradiated our system for 6 minutes. After that, we can see some oxygen ring on the surface of the packaging, and we exposed this brush surface to the para-anisidine through a ring opening reaction, and we immobilized the para-anisidine on the surface of the packaging. After that, we applied as an antioxidant for two different materials. One is the biomedical materials, and second is the food matrix. The chemistry of the packaging surface, we investigated the chemistry of the surface with the FCR and NMR. We can see after grafting of the GMA on the surface of the PP, we have a new peak. Those peaks are corresponded to the GMA. And when we expose the brushed surface to the conducting polymer, also we can see the characteristic peak of the para-anisidine. In the NMR also, this is the solid state NMR, just about the chemistry of the surface. We can see the chemical structure after photografting and after immobilization of the para-anisidine on the surface. This type of the surface modification is restricted to the shallow region nearby surface, so we don't interfere in the packaging structure, and we maintain the packaging structure in whole of the work. We further analyzed the chemistry using XPS. We can see that after photografting, we don't have a nitrogen peak. This nitrogen peak is belong to the para-anisidine. So after immobilization, we have these elements on the surface of the film. In here also, we can see a different chemistry of the PP film, brush surface, and antioxidant film. The morphology of the film was analyzed using the AFM axem. We observed the surface by these machines. We can see in the PP film we have a smooth surface, and after photografting we can see the pore-like structure. That pore-like structure is the self-assembly photopolymerization of the monomer on the surface of the PP. And in the AFM also we can see the surface is a dense brush. The brush surface with the with brush morphology is versatile to immobilize the functional materials on the surface. In the last image, we can see the para-anisidine was immobilized on the surface of the brush surface. Here we check the free radical scavenging properties of the film using the DBPH method. We can see the our film showed antioxidant and free radical properties, and we analyzed our film also using a cyclovoltammetry to check the oxidation and reduction peak. Those data can show the film has an antioxidant and free radical that our system can reduce the hydroperoxide value, because hydroperoxide is the byproduct of the oxidation, and reduce and actually retarded the vitamin C degradation over the storage. This study was intended to develop the non-migratory packaging. So we investigated the film using EU standard for migration. we use two different methods to detect the migrated residues, but we couldn't find using a gravimetrical analysis and UV spectroscopy. So this data can confirm the system didn't leave any residual materials after the incubation with the biomedical materials. The work in here was intended to develop a new generation of the packaging for preventing the health challenge or some kind of the migration in the biomedicals and preventing the interfering the packaging properties. We applied these materials for the different food matrix, and we think it could be a new items for antioxidant, a good alternative for a migratory antioxidant. So in here we couldn't present all of the data. So if you are interested in our work, you can check the reference in here. Thank you for your listening.
Can I have a? Yeah. It's not a scientific question. It's just some kinds of, as you know, nowadays we are moving to some kinds of environment friendly.
Yes.
So in Europe, there are changes some kinds of change of the plastic bag is to just paper, you know.
Yes.
So this kind of film and butter is didn't have nutrients and any some problem in our environment. So what do you think about that?
Actually, moving from the plastic to the paper is a really ongoing and it's still debatable. You say controversial. Some scientists say this is a good way. Some say no, because paper will not give you a perfect packaging. Because paper doesn't have a good barrier properties, and because when you go to the market, you want to see your product inside, but paper is not transparent. So it's really important. But yes, paper is good. But if you want to use a paper as a packaging, you need to coat by plastic. So this is not paper anymore. It's a same kind of the multi-layer. Paper still needs more work for to be a perfect packaging. But in the case of our work, this is the plastic, and we use the polyolefin polymer. The polyolefin polymer is really convenient for recycling, so we try to change change the surface. I mentioned in here we just change the surface shallow region. We don't want to change the backbone. We don't want to redesign the chemical structure. So I think even this is some kind of the material we add, but I think totally our system can be, I think it could be a kind of the eco-friendly material, but we need to, because it's just assertion, we need to stand by this one by a scientific reason. But I think it's better than incorporating some material to the matrix. At least it's better than this one. But for supporting my work, we need to do better. But I think this approach is better than previous one. This one, this method is really versatile. Actually, we are the first research group in the world. We are, because photografting is used in the biomedical, in the engineering, but in the packaging, we don't have this kind of the technology. So we move to this technology. We can use a different method. We can use a deep coating, spray coating, casting, or multi-layer. Technically, packaging is a multi-layer material. We can use a different polymer, sometimes polymer with metal, with the paper. So in our system, but it's just one material. In this monolayer.
Okay, we move to the next presenter is from Iskra University and Mandani Labens. We will play by video, and the title is Control of a Schottky barrier, height of a nickel beta gallium oxide Schottky barrier diode by insertion of graphene layer. So the video will be start 2:15 exactly. So
Annyeonghaseyo. Firstly, I'd like to thank Committee of Advances in Functional Materials 2021 for accepting our work. I am Labad Madani. I am a PhD student in Biskra University from Algeria. I am working on wide and ultra-wide bandgap semiconductors devices. In this presentation, I will present part of our research, which is titled on control of Schottky barrier height of nickel beta gallium oxide Schottky barrier diode by insertion of a graphene monolayer. This work, prepared by me, Labad Madani, Professor Nordin Sangoga, and Professor Afak Mufjah from Biskra University, and Professor Isram Karim from Sejong University. Initial studies on gallium oxide were performed in 60s of the 20th century, but then it was almost forgotten for about 3 decades. An intensive research in physics, devices, and applications of gallium oxide in last decades placed that compound in front line of an ultra-wide bandgap semiconductors development. The excellent intrinsic properties of this material include an ultra-wide bandgap of about 4.8 electron volt, high electrical breakdown field, and high electron saturation velocity combined with availability of large-scale production from melts. In addition to its low cost compared with silicon carbide and gallium nitride, gallium oxide has 6 polymorphs, but beta polymorph is the most stable. However, gallium oxide has serious drawback of developing p-type semiconductor. Therefore, it is used mostly in unipolar devices such as MOSFETs and Schottky barrier diode. In last years, the number of gallium oxide Schottky barrier diode related academic publications has substantially increased, and researchers aimed from these publications to developing a high performance Schottky barrier diode with, for example, low series resistance, low threshold voltage to minimize heating during operation, low leakage current, and high thermal stability, and finally controllable Schottky barrier height. According to Schottky-Mudge rule, a linear dependence between Schottky barrier height and metal work function However, measured Schottky barrier height is not related to the metal work function as predicted by Schottky-Much rule. Farzana and coworkers, Yao and coworkers studied effect of metal work function on Schottky barrier height variations of gallium oxide Schottky barrier diode, and as presented in figure 2, a high deviations of measured Schottky barrier height from Schottky-Much rule. These deviations related to effect of interface states. Among the proposed solutions to reduce the effects of the surface states is deposition of an insulator between metal and gallium oxide. Bhattacharya and coworkers proposed deposition of silicon dioxide in interface between metal and gallium oxide. Then effect of metals on Schottky barrier height variations are studied. For example, Schottky barrier height for nickel is higher than that for platinum, although the platinum work function is higher. So Schottky barrier height values are not predictable. Another solution proposed by Harada and coworkers, they proposed deposition of flyer in interface between metal and gallium oxide. This layer consists of a mixture of palladium and cobalt oxide, as presented in figure 3. And as presented in figure 4, Schottky barrier height increases with interlayer thickness. In this work, a proposition based on insertion of a graphene monolayer between nickel and silicon-doped gallium oxide, as presented in figure 4. Thicknesses and properties of the simulated layers are presented in table 2. Now, in order to achieve the mentioned structure, Silvaco TCAD was used. In this simulation, thermionic emission, turning through graphene monolayer, and Shockley Reed Hall and other models were considered, in addition to traps related to considered layers. One graphene monolayer was considered the Schottky barrier diode outputs affected. For example, Schottky barrier height decreased from 139 to 0.43 electron volt. Threshold voltage decreased from 1210 to 100 millivolt, and also a decrease in series resistance from 5 to 14 milliohm centimeter square. However, an increase in leakage current as presented in figure 6. These variations are related to increase in turning rate as presented in figure 7. We demonstrated that insertion of a graphene monolayer enhances Schottky barrier diode outputs by increasing turning rate. We have now to take into account possibility of tuning graphene bandgap and work function. These characteristics of graphene used for controlling Schottky barrier height, as we will discuss. Firstly, graphene bandgap was studied. When graphene bandgap increased Schottky barrier height, series resistance and threshold voltage increased as presented in figure 8. And as presented in figure 9, when graphene bandgap increased, an increase in leakage current. These variations in the Schottky barrier diode outputs parameters are related to decrease in turning rate when graphene band gap increased as presented in the inset of figure 9. Another important parameter is the graphene work function. So when graphene work function increased, Schottky barrier height increased from 0.35 to 0.62 electron volt. Threshold voltage increased from 20 to 270 millivolt. In addition to an increase in series resistance from 0.73 to 165 milliohm centimeter square, in addition to a decrease in leakage currents as presented in figure 10. The increase in Schottky barrier height and threshold voltage interpreted according to Schottky-Mott rule as presented in equation 2, and the increase in series resistance and decrease in leakage current related to decrease in churning rate when graphene work function increased as presented in the inset of figure 10. In summary, the effect of graphene monolayer on nickel beta gallium oxide Schottky barrier diode are studied. When graphene monolayer inserted a decrease in Schottky barrier height, series resistance, and threshold voltage. These variations are related to an increase in churning rate when graphene monolayer was inserted. Then effects of graphene band gap and work function were studied. An increase in Schottky barrier height, series resistance, and threshold voltage with churning rate decreasing in a graphene monolayer. In conclusion, we can tune Schottky barrier height and other Schottky barrier diode parameters by tuning churning rate in a graphene monolayer. And thank you for your attention.
Questions? Maybe if you have any question, we will reply by email. So we move to next presentation. Next presentation is Chungnam University, Sung-gil Yoon, and the title is Direct Growth of Highly Conductive Large Area Stretchable Graphene.
Okay, good afternoon. Okay, my name is Sun-gil Yoon from Chungnam National University, Korea. Okay, so I have many results, but I wanted to reduce the 55 for 15 minutes. So this is a topic is a direct growth of highly conductive large area stretchable graphene. Okay, so this is overview of my talks. I use titanium bottoms for graphene synthesis at low temperature. So many researchers use for the graphene growth onto the nickel and copper at the high temperature of 1000 degrees C. But in my case, I use titanium buffer films at 100 degrees C without transfer. So first of all, I will talk about the 4-inch and 8-inch wafer scale graphene synthesis at 100 degrees C by plasma oscilloscope CVD. Second is a large domain size. That means we can make a single crystal and polycrystal graphene FET device. So using the control of the channel dimension. So finally, today's talk is highlight is a predominant stretchability of monolayer graphene and graphene FET devices. So as you know, this is a titanium properties. Titanium buffer is very stable at the high temperature in hydrogen and methane gas atmosphere. And then titanium metal is rapidly oxidized titanium dioxide under the air ambient. So in the case, this is a titanium O2-X. This is a semiconducting property, not insulator. And then this one is also, we develop titanium and take out the air ambient. This is titanium dioxide. In the case, so titanium dioxide is not influence on the transmittance of the substrate. Because of that, so we use the titanium buffer layer on graphene rods, take out, so on the layer of the titanium, you change to titanium dioxide. Because of that, titanium dioxide is not influence on the graphene properties. Okay. So this one is, but we should make a critical thickness of the titanium buffer. As you can see, this is a glass transmittance and 5, 10, 20, 30 nanometer with increased titanium thickness and transmittance decrease. And then sheet resistance also, so above the 220 nanometer, this is a rapidly decrease of sheet resistance. That means, so we should make a critical thickness below the 10 nanometer thickness. That's very important. So now, so we have a feasibility test for the graphene growth, the titanium buffer deposition, and the CVD. So we already published ACS Nano Journal. Now this is one system. So titanium deposition by sputter and plasma CVD. So because graphene is very severe damage from the plasma atmosphere. Because of that, we make substrate and plasma is very so 10 centimeter so far from here like that. So we can make a titanium deposition by sputter and graphene growth is at the same time. So this is we make a Raman result of the 150 to 80 degrees C. So you can see that all of the graphene show the monolayer. And then, so IDG and ID2G is very nice result. So reported best value from the transport graphene. So 2D band and G band is very large. That means, so not crystallinity is not good for the transport graphene, but in our case, very small of the after HM of 2D and the G band. This means a very high quality of the graphene at low temperature. So our graphene should be discussed with some mechanism. So we have two different mechanisms. One is a gas phase and surface relation control mechanism. But in our case, this is a mass transfer gas transfer mechanism compared to the surface relation control mechanism at high temperature. So you can see that this is a mass transport gas mechanism. And then we can measure the sheet resistance mapping. So 6 centimeter like that. So 78 to 83. That is a very, very low sheet resistance of our graphene. So this is very easily checked for the sheet resistance. This is a 4-inch scale packed flexible substrate grown at 100 degrees C. This is 75 to 81 ohm per scale. This is a very sublime data. So as I mentioned before, this underlying titanium buffer layer on the ambient air, after graphene grows onto titanium buffer, this is a titanium, all of titanium is changed to titanium dioxide. So because of that, titanium dioxide cannot influence on the graphene property. So this one is a transferred graphene without titanium dioxide layer. So we are using our graphene without the titanium dioxide layer. In the case of transfer process, they have some defect is there. And then, so sheet resistance is almost 100, or a bit higher than in situ graphene growth. And then we make a FET structure for Dirac voltage. So our dielectric graphene growth is a 0 voltage. There is no doping, but transformed graphene have a bit, so 1 point voltage positive shift. That means that P doped by the transport process like that. Okay, so this is a surprising data. This is our graphene domain size grown at 100 degrees C. This is a very high, very large. So this is every domain size of graphene is 380 micrometer. So you cannot see any graphene for the transformer. So this is very surprising data. So from that one, we make a FET structure. So we calculated some mobility using the gate, the transfer or line method. So this means we change the channel length for the graphene mobility. Okay, so we can make a total resistance and the sheet resistance and the contact resistance. We can calculate as a function of the channel length. So channel length is below the 100 micrometer to 3 micrometer, very small range. So in that case, as I mentioned before, so we have a very large domain size. Because of that, we can make a FET structure inside the domain. That means a single crystal. So FET, and then dual domain and multi-domain like that, this is a polycrystal. So FET, we can divide it like that, okay? And then, so we measure the transfer curve, so we can clearly see that this is a single crystal, this is a polycrystal, okay? So in the single crystal and the polycrystal is left clearly divided into the like that. And then we calculate the graphene mobility. In a single crystal case, almost 40,000 femtosecond per volt second. This is a very large. And then, so interesting is now, so everybody knows the graphene have a very large mechanical strength in the planar direction. Okay, so because of that, so stretchability is very, very low. So almost they reported that 11% stretchability is maximum. But because of that, we cannot use for the skin has some other bio or electrical devices using the graphene. This is a limitation. But in our case, you can see that this is 70%. So stretchability right there. Okay, and then we can check the illumination. This is a blinking. So 70% is blinking and 90% stretching and recover. So completely recover. So transformed graphene shows almost 6% recover. Well, in our case, is 90% is also recover here. So we can, so how? So why our sample have a large stretchability? We have two different ways. One is, so a large domain size, so increase the fracture strength of the graphene. This is already Korean guy published a science journal. Depends on the fracture strength, depends on the domain size. So in our case, there's a very large domain size. So one reason. Second reason is, so we can show that this is, so our graphene grown onto a titanium buffer layer, take out in the air ambient. So titanium is a titanium dioxide chain like that. And the interface of TiOC. This is a bridge layer is there. Because of that, This one is the influence on the high stretchability of the our graphene here. So I can compare with the this is a blue one is a reported graphene. This is a transport graphene, and then so Nature journal. So this is a very low. So 20% and 30% is rapid increase of the reasons. But our transport graphene, this is a without titanium dioxide layer, or a bit increase like that. So this means that our graphene have a large domain size, improve the stretchability. But this is with TiO2 minus 2 minus X, that means the TiOC bridge layer is very large, so stretching straight like that. Okay, so this is a critical view. So okay, so in that case we can make a FET, graphene FET, so structure. FET structure is very, very complicated. The substrate PDMS and bottom graphene and the interfacial layer PI, the gate oxide, and graphene active layer, and the source range also graphene. There are so many layers. That means we force the stretching force, and that force is divided into the layer. Because of that, we can expect the high stretchability of the graphene FET. So we can calculate that. So this is, we measure the gate voltage of 4 voltage like that. In that case, whole mobility is 20,000, already lower than the 40,000. Because of that, that is a SI of SI. It is a so stick the substrate. This is a PDM is very, very flexible substrate because of the lower. And then, so this is a 140% of the stretchability of the graphene FET. This is a very surprising data. Okay, so we can check the cycling number is 5,000 cycle of the 140%. So ferrous strength, that is a still steady state like that. So our graphene have a very high stretchability, but I cannot show the flexibility now. So we already so published the Nano Today journal that is almost 15%. So stretchability, no, the flexibility also. So our graphene have stretchability and flexibility results. So if we use our graphene for the foldable smartphone, so we can use our graphene possible too. Okay, and this is my final data is. So this is a summary. Thank you.
Thank you for your presentations, and any questions? I will make one question here. You mentioned about graphene, FET, and very large stretchable and high performance transistors. So this kind of device you mentioned about that can be applied in kind of biosensor or any other things. So the graphene is the gross temperature is almost 1,000 Celsius. But now you mentioned very low temperature growth. So is there any difference between the high temperature graphene and your graphene? Should be there are some difference and
okay.
issues. Yeah.
Okay, so first of all, everybody use for the copper and nickel metal cathode material. But in the case, there is a growth mechanism different. So at the high temperature in hydrogen atmosphere, and the copper in nickel is not stable. There's a bit some poise formation, and then methane gas is decomposed to the carbon is penetration into the copper and nickel. In that case, there is a high temperature need for graphene growth because they governed by the surface reaction control mechanism. But in our case, there is a mass transfer control mechanism. That means even though the temperature is very low, and then too many carbon supply, that is very easy to graphene grow because titanium and carbon is matching is very good. And then, so that is activation energy is very low, 0.28 electron volt. Because of that, it's very easy move to the graphene growth. Okay? But at high temperature growth, graphene should be transferred. Because of that, they have many defects. But in our case, so we don't need to transfer. Okay? Why? So titanium changes to titanium dioxide, that is not influence on the electrical property of the graphene. So this is a very important. Everybody. So need for the. So now I transferred my technology to the graphene company. They produce the 13-inch wafer scale and alpha. So production now. Okay. This is very important.
Okay, let's finish and move to next presentations. So next presenter is from Jeonnam National University, and presenter is Chen Lee, and the title is Morphologic Control of Electrospun Polymer Fibers Using the Water Controller. Will be played by video.
Hello everyone, my name is Session-1. I'm a PhD student from Jeonnam National University. Today I'm going to talk about one of my ongoing research work. is the morphology control of electric bond polymer fibers using a water collector. Here are the contents of my presentation, including the introduction, the fiber morphology control using the typical electric spinning process, and the detailed method in my case, and the results and discussion, finally the conclusions. First is the background. The electrospinning is considered to be the most successful method to produce fibers with diameters ranging from microns to nanometers because of its versatility and easy production of fiber with diverse morphology. In a typical electrospinning process, a metallic solid collector is employed. Due to its good electrical conductivity, fibers can be accurately deposited on its surface. By properly designing the collector, the required fiber morphology can be obtained. The liquid collector can also be applied to electric spinning. This technique is called wet electric spinning. It was developed to produce three-dimensional structured fibers and stand-alone fibers mass more efficiently. Below two figures shows the schematic of the electric spinning setup. In the left side is the typical case. In the right side is wet electric spinning case. The fibers with its various morphologies are well developed in typical electric spinning. However, most are limited to the use of solid collectors. In addition, the production of fibers with different morphologies requires the design of different types of collectors, which is not efficient. The use of liquid collectors in electric spinning can also produce fibers more effectively with diverse morphologies, such as fiber yards and circumferentially aligned fibers. However, the liquid collectors have not attracted much attention in previous studies. Furthermore, in previous contributions, a stick-thick liquid collector was used, which is the most basic form. It limits the manufacture of fibers with diverse morphologies. The in-depth research on the electrospinning liquid collector is necessary for the production of fibers with various forms. It is also important to comprehensively investigate the interaction effects of the liquid collector and the electric spun fibers on the fiber morphology. This figure shows the schematic of the electrospinning setup used in my study. It can be found that different from the typical wet electrospinning only using the static liquid collector, a metallic stir was employed to provide the rotational motion of the uh, water inside of the collector. Two interactions was investigated in my study, as summarized in the right side, the hydrodynamic interaction, which is the effect of flow velocity of the liquid collector, and the electrical interaction, which is the effect of the conductivity of the liquid collector. and their effect on the fiber morphology, including the fiber mat size and density, the fiber diameter, and alignment, was investigated. The first column in the first figure, the aluminum foil, represents the typical case as a reference, and from 0 RPM to 900 RPM is the using of the liquid collector with different rotation speed. It can be found that compared with the typical solid collector, a larger fiber mat size could be obtained when the liquid collector was employed. In addition, it was found that as the rotation speed of the liquid collector increased, the size of the fiber mat also increased until the 900 RPM case. It can be found that compared with the 600 RPM case, the 900 RPM case, the fiber mat size was not increased. Instead, it was reduced. As shown in the insert in the last column 900 RPM case, it can be found that many fibers were fused at the center region of the fiber mat. This may resulting in the reduced fiber mat size compared to the previous case. And because the fiber mat deposit on the liquid surface can be move with the liquid collector, and as the rotation speed of the liquid collector increase, there is a vortex generated on the center of the container. Further increase the rotation speed, the further increase the size of the vortex was also increased. It makes that the deposition area of the fiber increased as the rotation speed was increased. This is maybe the reason of that as the rotation speed from the 0 to 600 RPM was increased, the size of the fiber mat was also increased. And in this research work, only the general change trend of the fiber mat size was considered. So in the 900 RPM, it will be not considered in this specific case. And the red side shows the relationship between the rotation speed of the liquid collector and the fiber mat density. It can be found that as the rotation speed of the liquid collector increased, the density of the fiber mat was also reduced. It can be found that it's consistent with the results with the fiber mat size. As shown in the left schematic, away from the center of 10 millimeter was selected as the starting region of the measurement, and each region has 5 millimeter. So in a single sample, 3 regions, namely region A, region B, and region C, was selected, and in each region, 4 points will be measured. So in this manner, totally 12 points was selected in a single sample to quantify the properties of the fibers. And in red side is the results of the relationship between the rotation speed of the liquid collector and the fiber diameter. It can be found that as the rotation speed of the liquid collector increased, the diameter of the fiber was also reduced. It can be explained that because the fiber deposit on the liquid collector surface move with the liquid collector, and this kind of movement will further stress the fiber, resulting in the reduce in the diameter of the fiber. And the higher rotation speed means this stressing effect is more significant. So the smaller fiber diameter can be obtained at the high rotation speed. In addition, It was found that the diameter of the fiber gradually increased from the center to the outer region in the 6 and 900 RPM cases. It can be found that the rotation speed of the liquid collector has a significant effect on the morphology of the fiber for the same observation region. Similarly, at the same rotation speed of the liquid collector as the distance from the observation region to the center of the vortex change, the morphology of the fiber also changes. When the rotation speed of the liquid collector is increased to 600 RPM, as shown in figure G, H, and I, some fibers begin to align. In the first figure, the conductivity of the liquid collector 2.65 represent the neat water collector, and from the second to the fourth case is the increase the conductivity of the liquid collector, and in the last case is the electric liquid case. Because during an experiment we found that some fibers was immersed into the electric liquid, so we also don't consider the electric liquid here in this specific case. And it was found that the conductivity of the liquid collector also has a significant effect on the size of the fiber mite. It can be explained that as the conductivity of the liquid collector increase, more fibers can be deposited on the same region, because the charge accumulated on the deposit fiber can be quickly transferred as the conductivity of the liquid collector increase. This results in the reduce in the fiber mite size as the conductivity of the liquid collector increase. It was found that there is no significant effect on the diameter of the fibers when changing the conductivity of the liquid collector. And finally, the combined effect was also investigated. As shown in the first figures, the LR represent the low rotation speed, the HR represent the high rotation speed. Similarly, the LC represent the low conductivity, and HC represent the high conductivity. And the right side showed the corresponding as images corresponding to the left figures. It was found there that there is no significant effect of the liquid collector conductivity on the fiber diameter for the rotation speeds considered here. In contrast, under the same conductivity of the liquid collector, the change in the rotation speed of the liquid collector has a significant effect on the diameter of the fibers. So finally is the conclusion. This work outlines a precise morphological control of the polymer fiber that is electrospun using a rotating water collector. The hydrodynamic and the electrical interaction between an electrospun fiber and the liquid collector was investigated to show their effect on the morphological properties of the fiber. The experimental results showed that the hydrodynamic interaction plays an important role in determining the size and density of the fiber mite, and the diameter and the arrangement of the fiber. The electrical conductivity of the liquid collector was found to influence the size and the density of the fiber mite. The present research can be employed as an efficient tool to control the morphology of the electrospun fibers, thereby promoting their potential applications. That's all for the presentation. Thanks for your attention.
Okay, this is a video presentation, so if you have any questions, you can contact directly and he will reply to you. So move to next presentations is the same university, Jeonnam National University, and the presenter is Sun. The title is the development highly water resistant and strong microfibrillated cellulose film as a green platform.
Here is outline for this presentation. It consists of 5 sessions. First, I will give you a brief introduction about neural materials. From that, we will determine my research objectives. Then, I will present about my experiment. And next will be the results and discussion. The final will be the conclusion. Yes, in the first session, xenon is most abundant renewable polymer on Earth. It can consider as almost inexhaustible, sustainable natural polymers. From the three main resources, plant, agricultural, waste, or unused, are three main resources of cellulose. From these raw materials, the nanocellulose is made. Basically, there are two kind of nanocellulose called cellular nanocrystal synthesis and nanofibrillated or microfibrillated cellulose NFC or MFC. The main difference between synthesis with NFC or MFC is that synthesis just have a crystallized domain, while the NFC or MC have both crystalline and amorphous domains. Because Lacino have many advantages. For example, it's very high strength and stiffness. It has low density, its biocompatibility, biodegradability, and sustainability. So it has many potential applications such as green composite, electronic device, coating, packaging materials, medical implant, or filtration. Some feasibility of applying nano in practical applications has demonstrated, such as in thin film transistor, in solar cells, or the biosensor. However, this nano has some limitations, such as it's very poor water resistant. Some research shows that the waste paper, after immersing the napa in water for 24 hours, its thickness increased 200 times. A waste strength of nano paper was very low, the 2.3 megapascal. The second limitation is very bristleless. For example, the elongation of nano is 2.14%. Therefore, I determined my research objective is that development of highly water resistant, strong and flexible microfibrillated cellulose film using glycerol and hot pressing treatment. And here's materials. I use MSc material from my university. It has gel type consists of approximately 3% of MSc and glycerol 99% from sigma and rich. And this figure shows the procedure for making MSc film. Two sets of MSc film were made, AMSc and SMC, at different glycerol concentration. A and S means different drying methods. A is air drying, S is drying by hot press. 300 grams of MC suspension over 25% were mixed by magnetic strider for 2 hours. After that, the wet sketch of MC was obtained by vacuum filtration. Then wet MC is immersed in 1, 2.5 and 5% glycerol solution for 24 hours. Finally, the AMC or SMC with different glycerol concentration we obtained by air drying or hot pressing treatment. First, to confirm the components of glycerol with MSc, we use the FTER analysis. you can see here. Forms that you can see for list AMC and list SMC has a similar FTEI because there are no chemical modification. Has a peak as 3288 and 1662 are due to the hydrogen groups in the Latin rule. For platicide AMC and platicide SMFC, cases the peak in range of the 2010 to 3650 and 1662 are greatly enhanced due to the hydrogen groups in glycerol molecules, and also the double peak as the 2879 and 2929, and the absorption peaks around 1110 and 1028 are characterized for glycerol molecule. So we can see that glycerol is composed with MFC. Then compare between the SMFC and SMFC. The absorption peaks of SMFC are weaker than those of AMFC because there's a lower glycerol content in the platicide SMFC. To investigate the mechanical property, we conduct the tensile test using the dot bond shape. The testing were conducted at the two states, dry state and wet state. In the wet state, we can obtain the wet chain of the MSC film. And here is the result of the dry tensile test. From this figure, stress change curves, we can see least SMFC achieves the higher tensile strength compared to the least AMFC because the hot pressing treatment makes the denser structure and making additional hydrogen bonds. Hence, generally, adding glycerol, we can see adding glycerol will reduce the chance, mechanical change and genres while increase the change at price. In this figure shows the effects of tensile chain elongation and jump modulus according to the glycerol concentration. Interestingly, the case of MSC 2.5% G shows piezo behavior. It's increasing the elongation while maintain the strength. It can explain by the two effects of glycerol when combined glycerol and hot pressing treatment in SMFC. First is platicization effect of glycerol, which reduces the strength. And the second is the forming of additional hydrogen bonds between glycerol and lactanool, also between glycerol to glycerol molecule during hot pressing treatment, which will be increasing the strength. So in the case of MSC 2.5% Z, the positive effect exceeds the negative one. That's why it shows very special behavior. Water resistance is very important for MSC films. To characterize the water resistance of MSC film, we use the measure the water absorption, chaining thickness, and wet chain. And wet chain is obtained from the wet tensile test. For water absorption and chaining thickness, we immerse the sample in water at 25 centigrade for 24 hours. Thus, the excess water were removed. Then the thickness and mass of sample were measured immediately before and after immersion in water. And using this equation, we can calculate the chaining thickness and water absorption. In this table shows the water absorption and chaining thickness of list AMC and ADMC. It shows that list AMC exhibits very high value of water absorption at 137.4% and chaining it at 79.1%. And the list AMC shows the great improvement. Then it proves that the hot pressing treatment show various positive effects on water absorption and change in thickness. This figure shows the effects of glycerin concentration on water absorption and change in thickness. For AMC, yes, it clears that glycerin increased significantly. You can see the water absorption and change in thickness. But for SMC, this effect is more complicated. Glycerin show positive effects at low glycerin concentration here, but negative one at high glycerin concentration. And the SMC 1% G shows best value. Here you can see what option is 30.9%, and the changing is 56.3%. And here this figure shows the west chance of HCAMC with different glycerin concentration. From that you can see the west chance of least AMSC was very low, 3.2%. And also adding glycerin will further reduce the west chance of AMFC. The west chance of SMFC, least AMFC, is significantly improved compared to the least AMFC. The effects of glycerin and hot pressing treatment on west chance of the SMFC is quite a little complicated. It has positive effect at low concentration and negative effect at higher concentration. And also, in the case of SMC 1% G, it shows the maximum west chance at about 45.7 megapascal. So, is sustainable. Therefore, this modified MC film can be used as a green, strong, and flexible platform for advanced applications such as printed electronics, filter, or in the platform for biosensor. This work was supported by National Research Foundation of Korea. This is the end of my presentation. Thank you for your attention.
Also, if you have any questions, please contact directory and he will come back to you. And let's move to the next presentation is printable giant magneto-resistive sensor for highly compliant on-skin electronics. It's coming from the ETRI. Present name is Min Jung-ha.
Hello everyone, I'm glad to meet you with this virtual meeting. My name is Min Jung-ha and I belong to Electronics and Telecommunication Research Institute in South Korea. The subject that I talk to today is the highly compliant and printable giant magneto-resistive sensors for the application of the human interactive on-skin electronics. The development of the flexible magneto-resistive sensors is important for the recognition of the environmental changes, tracking position, bodily motion, and gestures with the touchless manner. Therefore, many types of magnetic field sensors have been proposed with bendable, flexible, stretchable, wearable, and imperceptible design for the use of the human interactive electronics such as electronic skins, wearable electronics, Internet of Things, soft robots, and virtual reality. One of the effective methods to develop the flexible magneto-resistive sensors is based on the printing technologies, which have a lot of merits for low cost, large area production, and easily adaptable to the various material and freely defined layout. So there are several approaches for printing magnetoresistive sensors by using the magnetic nanowires or magnetic paste. However, they are still premature to apply for on-skin magnetic field sensors because their limited flexibility restricts the skin conformer property. Another issue is to achieve the high sensitivity in low magnetic field range without posing any risk to human health. Therefore, we suggest the highly compliant magnetic field sensors based on printable giant magnetoresistive paste, so-called GMR paste. For the preparation of GMR paste, we fabricated the 30-layer permalloy copper thin film and further exfoliation and sonication to transform the microplates. It could be well mixed with the binding polymers for the viscoelastic GMR paste, and this GMR paste is easily printed and strongly adhered to any substrate. Also, the fast evaporation of the sorbent in the binding polymers makes the extremely volumetric shrinkage and high percolation network between the microplates. So you can see this ultra-thin GMR sensor, which is conformally attached to the human skin. In addition, this printable GMR sensors has high flexibility, which can be bent up to 16 micrometer of bending radius with high GMR performance and sensitivity. Now we have to consider why we need the 16 micrometer of bending radius. Simply to be attached on skin, we don't need such a small bending radius. However, to be applied for on-skin electronics, the magnetic field sensors should endure until the extremely compressive and stretchy stage on the complex and wrinkled surface of the skin. So we prepare the stretchable GMR sensors on the pre-stretched Ecoflex. The printed GMR sensors induce the wrinkled surface from the compressive force when the pre-stretched Ecoflex was released. Therefore, this highly compliant GMR sensor represents a great mechanical stability and magnetic field sensing capability under 0% and even 100% of stretching state. As I mentioned before, we should achieve the high sensitivity in low magnetic field range that is applicable for the on-skin electronics in daily life. So we standardize the magnetic field sensitivity divided by the detectable field range as a figure of merit. When we compare the flexible magnetic field sensors, our GMR sensors based on permalloy copper microflakes with second antiferromagnetic maximum has 150 times higher sensitivity at 0.88 millitesla of small magnetic field, where the field range can cover the wearable electronics for daily use. With the same printing method, we can cover the intermediate field range with high sensitivity by using the cover copper microflakes-based GMR sensors for the consumer electronics. So our printable GMR sensors have great potential to cover such a broad range application to overcome the limited usability of existing GMR sensor. To evaluate the stability of our GMR sensors for the use in daily life, we characterize the operational temperature range and magnetic field sensing performance at the different angles. Most of the pastes have problem of a high thermal expansion coefficient of binding polymers, but the high density and well-distributed microflakes in the polymer provide the superior interference of the heat dissipation up to 90 degrees Celsius, where the range is enough to operate on-scan electronics and consumer devices. And thanks to the multi-axial alignment of GMR microflakes compared to the stacking morphologies, our printed GMR sensors provide a similar GMR ratio regardless of the magnetic field direction and isotropy sensing performance without degrading the sensitivity under in-plane and out-of-plane field. This omnidirectional sensing capability provides the great benefits for freely locating GMR sensors on scan without spatial pre-positioning of the magnets. Here we demonstrate the applications of our highly compliant and printable GMR sensors for remote control system, where the sensor attached on the human fingertip and hovered over a small permanent magnet to control the virtual objects. Under this configuration, slightly approaching the sensors to the magnets produces a large enough voltage change to cross the predefined threshold 1, resulting in a scroll-up event. Further approaching to the magnets significantly increase the detected magnetic field and drives the sensors into threshold 2, which results in a scroll-down event. As you see these movies, this kind of interaction was used to seamlessly navigate over a doc file and zoom in and out of an interactive map pointing to the specific location. This demonstration highlights the potential of wearable and skin-mountable magnetic sensors to enable the remote control and touchless interaction in the low magnetic field range. In conclusion, we have demonstrated the highly compliant and printable magnetic field sensor relying on the giant magnet resistive effect. These sensors are capable of detection in low magnetic field below 1 millitesla and sustaining the high-performance magnetic resistive sensing under the extremely mechanical deformation up to 16 micrometer bending radius and 100% of stretching state. Due to this unique mechanical compliancy, our printed GMR sensors can be easily applied on skin, enabling the wearable interactive electronics that are suitable for the daily use by the public. So this sensor functionalized finger conducts the remote and touchless control of the virtual objects, which is manageable for the touchless interaction with a tiny permanent magnet. So we feature the potential of our highly compliant and printable magnetic resistive sensors in augmented reality settings, remote healthcare, biometric security system, prosthesis, and human-machine interface. And thanks to the members of Helmholtz Institute and support from the Electronics and Telecommunication Research Institute. And this work was supported by German Research Foundation and Korean government. Thank you for your great attention.
Okay, yeah. We have also have any questions, please contact directly. And today oral presentation session is finished, and the last presenter did not attend, so oral presentation is finished. So thank you for your attention. See you soon.
Okay, so let's just start the keynote session 2. Hello, everyone. I'm Jaeun Jang from Daegu Gyeongbok Institute of Science Technology. And we have the three speaker for this keynote session. And first speaker is Dr. Lu Jun-ma from the Nankai University. His presentation title is the application of flexible and stretchable electronics and solid state cooling based on functional polymers. Could you start your presentation, Professor Ma? Okay, we need wait for a while due to some technical issue. So could you wait for a while? 홍 교수님 먼저 하셔야 될 것 같아요. Sorry, would like to change the presentation order due to some technical issues. So, Professor John Hong will speak first for this keynote session. Professor Hong comes from the Kookmin University, and his presentation title is Room Temperature Synthesis of High Transparent Conductive Copper Sulfide Film via a simple sulfur activation method.
May I start or? Oh, greetings. Hi, my name is John Hong. And first of all, thank you for giving me this great opportunity in front of you guys to talk about my research accomplishment, interest, and in the room temperature synthesis of highly transparent and conductive and copper sulfide films via a simple sulfur activation method. I have involved in many different scientific projects, such as the development of structured and non-structured materials for their many different applications, especially transparent conductive electrode or energy applications, especially some how to find a new synthetic road to design those structured and non-structured materials are my main interest during my DPhil and postdoc and in Kookmin University. So let me briefly talk about my biography. My name is John Hong, and Korean Hong Seung-yeon, and right now I'm an assistant professor in Kookmin University in Advanced Material Engineering department. My research experience is mostly related to the synthesis and the characterization. And first one is the synthesis, analysis of nanostructured and non-structured materials, and characterization and understanding of electrochemical reaction mechanisms and applications with low-dimensional materials, which is strongly related to today's topic, and identification and synthesis of electronic and photovoltaic colloidal quantum dot devices. Until now, I am assigned to the various different assigned projects. One is in doctoral project is the 1D NEOM project in European Research Council, which is for the fiber-based material platform for flexible coding applications and different energy-related applications. UniQDs for the quantum dots and electro application, the hybrid and find the synergistic effect between the nanostructured materials and quantum dots for photovoltaic and light emitting diode applications. And third one is Samsung SAIT program, which is also strongly related to the 2D and quantum dot electronics. And I was in LBNL during my postdoc program. I was involved in the fast charging cell evaluation of lithium-ion batteries and advanced battery material researches. So before talking about my copper sulfide related projects, I was interested in about how to control the surface of sulfide quantum dots. And usually quantum dots are synthesized by the colloidal synthesis, and we need to add, maybe I can use it. I'm not sure you guys can see this or not, but during the colloidal synthesis, we need to use those kind of long chain oleic acid, which is supposed to be attached to on the surface of PB transient metal and the sulfide anions. And due to the existence of those oleic acid, we can precisely control the size of quantum dots, which are strongly corresponding to the band gap of those quantum dots. That is why the major advantage of quantum dot is a high tunable band gaps and large production based on the colloidal synthesis, and precise synthetic rows can be attained. However, when we make these quantum dots to the real electronic devices, those kind of long chains usually hinder the transfer of electrons from one quantum dot to other quantum dots. So during this project, my main topic is how to remove those kind of long chain oleic acid accurately within sustaining its original band gap properties. So the first one is we would like to change the long chain oleic acid to the iodine, the atom which is known as the single atomic sized molecules and single atomic sized compounds. And based on that, in terms of the solar cell application and its parameter, we can figure out all the related solar cell parameters like a PCs, short circuit current, shunt resist, and series resist. All those parameters which are strongly related to the electronic transfer have been improved well. So replacing existing long chain oleic acid with the halide ion for the better passivation and time-dependent halide exchange procedure to optimize the surface passivation was one of my research accomplishments in terms of quantum dots. And next one is hybrid ligand exchange. Even just using a one iodine-related atomic passivation is not perfectly cover all the location of quantum dot surfaces. So we need to find the other candidate to change this oleic acid. Then in that cases, we use the hybrid ligand exchange method. So finding an organic and inorganic compounds to passivate the surface of quantum dots. And in here, we use a pyridine materials with iodine. And for the characterization in terms of time result PL, and FTIR, we figure out the existence of oleic acid are strongly removed, and the excitons can be well maintained before the recombination. And finally, we can improve the solar cell efficiency between the non-passivated quantum dot films and hybrid passivated quantum dot films. So recovering based on using this two different hybrid ligand exchange method. By using this hybrid ligand exchange method, we can recover not perfectly passivated trap site on PBS quantum dot, and finally improve all the source related parameters. So after those kind of interest in the quantum dot passivation, I am also interested in about how to synthesize sulfide related materials, and which is strongly related to today's topic is how to design highly transparent and conductive transition metal sulfide electrodes. As you guys may know, TCs, a transparent conductive electrode, can be used in many different applications. First one is OLED, stretchable LED, solar cells, even TC heater, even EMI shielding, electromagnetic interference shielding application. All those TC materials and all those TC candidates should be synthesized and should be applied on the target substrate. And how to synthesize those kind of materials then, and for further pursue the research progress in this TC field, we need to figure out what kinds of material we are going to select. It can be a semiconducting material, and mostly for the TC, we need to find metallic material candidates. And somehow it can be a synergistic combination between inert and the metallic material for the stability under the flexible substrates. And we need to think about how to synthesize those kind of TCE or electron materials. We can use a hydrothermal or solvothermal method by using a solution-based synthetic routes, or combustion CVD method like metallic MOS2 or metallic graphene can be synthesized under this CVD. Or to design the nanostructure material, we can also use a colloidal synthesis. And finally, for the large deposition, electrode deposition is one of the synthetic candidates to make those kind of TC electrodes. And we also thinking about this TC can be usually used as the industrial target and industrial purpose. And to make it more possible to use in industrial purpose, there can be a like roll-through process as pre-ink preparation can be a two well-known effect for the practical fabrication. And finally, we need to check and we need to characterize the synthesized material are still successfully converted to our targeted materials or not. So various techniques like XRD, SEM, TEM, or PL, all those characterized technique has been used. And finally, those after the material selection, synthesis, and practical fabrication, the characterization, it can be applied in energy application like solar cells or other TC electrode like photovoltaic or light-driven sensors and all those different applications. And in this topic, we are targeted to make copper sulfide, the transition metal sulfide. And the reason why we are selecting the sulfide materials, there are many advantages of sulfide materials. First one is a high theoretical conductivity, and second is high applicability under a flexible system. So the future application has been changed and has been drawn to the flexible system, and all those TC electrodes should be on the highly conductive and transparent properties. Also, it can be well applied on the flexible, even stretchable substrate. So, what is the drawback of synthesizing those kind of sulfide materials? And as you guys can imagine, recently, all those sulfide synthetic materials are strongly related to the CVD method or solution-based method. All those methods require a high temperature treatment or a long time treatment to synthesize the structure and nanostructure sulfide materials. However, for the industrialized point of view, we need to find the other surface source which can convert a transition metal atom successfully and then fastly without heat treatment, might be a proper and a promising candidate to use those kind of sulfide materials in industrialization field. So many scientists still trying to use CVD and CVD and hydrothermal and sobothermal method because all those surfer properties and surfer candidates, surfer precursors usually require high thermal treatment. However, if we can find a proper surface source, except using the high temperature 3D surfer precursors, it will be really promising for to synthesizing those kind of transparent and conductive and transition metal sulfide materials. This is where we try to think about and how to make a progress in the sulfide materials. So what we find is a new surface source, which is induced from the ammonium sulfide solutions, and due to the property of the ammonium sulfide solution, they can induce H2S gas and ammonium-related H2 gas easily, and those kind of gasified H2S radicals can react the transition metals really easily due to its high activity. So basic schematic is we can deposit in this project we deposit copper films on the target substrate. For the transparent test, it deposits on the glass. For the flexible test, it deposits the copper film is deposited on the PET or polymer related flexible and stretchable substrate. And these copper films are the deposit copper films were directly exposed to the vaporized sulfur gas from the mentioned highly active sulfide solutions. And due to the highly reactivity between the transition metal, in this case copper, and sulfide gases, it can strongly the activity of H2S gas can strongly convert the copper from the copper film to the copper sulfide, from copper film to the copper sulfide film without any heat treatment and within the low time domain. In this case, for the further conductive enhancement, the converted CS nanoshade film on the substrate was a little bit annealed at 100 Celsius for 1 to 5 minutes. So after the schematic diagrams, as you can see here, copper itself is a little bit a 1 to 5 nanometer film thickness of copper film is deposited on the target substrate, and it is exposed to the H2S gas from the highly active solution within a short time domain. We figure out this copper film are strongly converted to the copper sulfide film without the heat treatment. And before talking about to understand the real mechanism of the sulfur corrosion of transition metal, we did the same sulfide exposure on the copper foils. And as you guys can see here more directly, visually, the copper foil, the brown colored copper foil can be turned to red colored copper foil after 5-second exposure, and after 30-second exposure it turned into the like bluish, a little green to bluish color copper films, and after 60-second exposure it turned to the a little bit bluish colored copper films. And we measured the in situ characterization of Raman and XRD after the each steps after the exposure, sulfide exposure. As you guys can see here, the basic index of copper sulfide usually show the vibration at 250 to 300. This is related to the copper atom and sulfur vibration, and the peak located at the 470 to 400 is a strong sulfur A1G bindings, A1G interference in this Raman spectroscopy. As you guys can see here, first one, let's see about the SSA1G peak differences. So after the longer exposure with this H2S gas on copper foil, we figure out the SS interference in terms of Raman spectroscopy has been increased a lot than the before. And second, we figure out it at 470 CUS vibration peaks are slightly shifted to the slightly shifted to the high range area. And this is usually mean the this is usually mean the successful conversion of copper films to the CUS films on the copper foils after 60-second exposure. Usually copper sulfide, interestingly, copper sulfide have been not researched, it is researched a lot in different applications, but the systematic control of the copper sulfide phase is a little bit hard because you guys may know there are very different but similar copper sulfide molecules can be exist. One is called the 1.96 sulfide, Cu2S, Cu1.96 sulfide, and Cu1.98 sulfide. And in this topic, we are targeting CUS materials. So in this case, we figure out at the beginning of the exposure, this copper foil converted to the Cu2S related phase. And after the longer exposure, the Cu2S related phase turned to the CUS phase, which is color like a bluish color on the Cu foils. We also determine the phase of the copper sulfide after the direct exposure of this H2S gas from the XRD measurement. As you guys can see here, 5-second and 30-second exposure copper foil films are strongly more strongly related to the Cu2S phase, and however, after the 60-second, it related to the CUS phase. So we can conclude that after this direct exposure, this CO film converted the Cu2S phase first, and then with the enough supplement of the sulfur atoms on this copper films, it can successfully turn into the CUS phase. So this is a transfer the CUS films from the copper foils. And we also figure out even the transferred copper sulfide films on the copper foils also show the similarly closely related to the CUS vibration as SS A1G vibration within the same material. So we can conclude that somehow the CUS films can be converted within the short time frame, like within the 60 seconds. So continuous surface supply from the solution and solution related H2S gas readily transform the pure copper films into transparent CS sheet films at room temperature. So main advantage of this synthetic findings and synthetic road is, if we can use only a simple solution-based materials, and this gas phase synthetic road can be well applied on the industrial use and industrial applications. To understand the sulfur atoms dissolution speed on copper foil films, we did the TOF SIM's the time of flight secondary ion mass spectroscopy after the each exposure times, and as you guys can see here, sulfur atom can be exposed, can be dissolved and diffused more in depth after a lot of expose more and then diffuse more in its depths according to the exposed time. And interestingly, the ratio of I, intensity of copper sulfide bindings to intensity of silicon bindings, has been increased according to the exposed sulfur sulfur gas exposure. So we can conclude that this sulfide exposure can be well diffused inside the copper films, and the thickness and the sulfide intensity, the sulfide diffusion length can be recognized by the intensity ratio between the CUS and the silicon intensity. And to conform, as I mentioned before, to confirm the crystallography and then the successful synthesis of copper sulfide films on after this exposure, we did TEM and XPS and PL measurement to determine the converted copper film is well matched with the copper sulfide. You guys can see here, we can see the and also we did AFM image. So different thickness of copper films are deposited on target substrate, and it is exposed to the H2S gas from the highly active solution. We figure out the height of each films are closely similar to the what is deposit, and there's a slight increase in thickness due to the copper sulfide film conversion. So due to this characterization technique, we figure out the atomic scale lattice image I mentioned in here from the TEM. We can identify this as a 100 axis orientation, and which shows the spatial distribution of the copper and the sulfur atoms, and well-organized honeycomb structure along with the corresponding spotty selected area ring patterns. You guys can see here in the previous pages, such as the atomically thin cobalt-like crystal of the as prepared copper sulfide after the large exposure time. And finally, the emission peaks is centered. The PL emission peak is centered at 450 nanometer, which is close to the reported PL emission peaks of the bulk copper sulfide and the ultra thin copper sulfide, demonstrating that after the separation process, the copper sulfide films can be successfully converted after the exposure from the H2S gas at the highly active solutions. So due to maximize this advantage in this conversion process, we can. So this is the first image in here. This three is we deposit the pure copper deposition on each side, and the partial left area is only sulfurized, and we leave this samples in the fumate, and we figure out the exposed sulfur and the converted sulfur, and there might be some overdosed sulfur can be diffused to the right side where only the copper film is deposited. So we can figure out, the sulfur atoms can be well diffused laterally and then vertically within the sea of films, which can successfully converted all the copper films into the CUS films. And to maximize this gas-related application, gas-related synthetic growth, as you guys can see here, due to its a simple fabrication method, we can successfully synthesize the CUS films on the large-scaled SiO2 substrate. So again, usually making and synthesizing sulfide material usually require high temperature synthesis, and due to its high temperature synthesis and solution-based synthesis, larger deposition of those materials are a little bit tricky, but by using our unique sulfur exposure technique, we can synthesize vapor scale copper sulfide films and samples successfully on the target substrate. For next one, we characterize the transparency and the conductivity of those copper sulfide films in terms of UVVs and sheet resistance, and IR laser transmittance and response time. So transmittance of CUS, the copper sulfide at 550 nanometer is clearly comparable to that of the ITO films, which are 96.1% and 90.7% and 79.4% for the 2 nanometer deposit copper sulfide and 5 nanometer deposit copper sulfide and 10 nanometer deposit copper sulfide respectively. And one of the advantages of this copper sulfide film is in this IR range. As you guys can see here, ITOs, the transparency in this region, within this IR region, is not that transparent. So the IR laser and all the light related to the IR wavelengths cannot transparent well within usually the conventional ITO films. However, within this copper sulfide films, it still shows more than 80% transparency over 10 nanometer deposit CUS films. So we we guess this kind of CUS transparent and conductive electrode can be used in IR related, infrared laser related applications. And we check the IR laser response time, IR laser response and response intensity according to the schematic illustration. We set the homemade IR laser and CUS quartz and IR detection characterization home kit, and we figure out compared to the ITO samples, 5 nanometer and 2 nanometer, 10 nanometer deposit copper sulfide film shows more transparency and a better IR response compared to the ITO films. And another parameter for the conductive film is the another parameter for this TCU film is the conductivity. After the surface exposure, the sheet resistance of those 2 nanometer and 5 nanometer and 10 nanometer thickness copper sulfide are slightly higher than what we expected. And this is because the simple surface exposure is not enough. The small time domain and the driving force for those kind of surface conversion is not enough to drive and to result in the highly crystalline copper sulfide films, which is strongly related to the conductivity of the materials. So after that, basically what I talked before in here, the copper sulfide films for further conductive enhancement and the crystallization, the converted CS films are annealed at 100 Celsius within 1 to 5 minutes. Within this high heat treatment, within this short and reliable heat treatment, we figure out the conductivity of each films are improved a lot, and the average sheet resistant value of CUS are found to be a 297.2 ohm per square meter and 94.9 ohm per square meter and 25.1 ohm per square meter respectively. And also the flexibility test. So we did a bending cycling test, and we measured the resistance comparison between the bending cycles and between the bending radius. As you guys can see here, after 10 to the 4 bending cycles, the original CUS can well maintain its original sheet resistant conductivity. However, ITO start to break its conductivity after 10 cycles, and the conductivity of ITO is increased almost 10 to the 3 times after 10 to the 4 bending cycle test. And also we tested the conductivity relationship between the conductivity and the bending radius test. The conductivity and the bending radius, conductivity versus bending radius test. If we increase the bending radius of the copper sulfide or ITO film, still they can well maintain its original conductivity up to the 2.0 millimeter bending radius. However, after the 2.0 bending radius, the initial conductivity ITO start to decrease, and we can simply figure out the ITO is not proper candidate for the flexible and transparent conductivity electrodes. And finally, it's an application. We made some application for this copper sulfide electrode on PET. Like we tested a bending test, a twisting test, and 100 cycle and 200 cycle bending cycle test. Due to the IV curve, all those original conductivity of CS films are well maintained, and even we are still working on optimizing the PL intensity and the quantum efficiency of the quantum dot LED, which is used with which is designed with the CUS electrode. So we deposit P.PSS, TFE for the whole transfer layer, and cadmium sulfide and zinc sulfide quantum dots for the light emitting active layers, and zinc oxide electrode and a aluminum electrode for the current collector. We figure out even using this copper sulfide film, it shows a red color LED lightning. However, we are still working on the optimization of the CUS films quality on this LED applications. And shortly, This highly active sulfide solution not just only can be used for H2S gas exposure. So what we did, just skip it. And my research interest is not only related to the TC and also related to the energy storage applications. And those kind of sulfide can be used in the supercapacitor materials. And my group and I work on a special class of electrochemical reactions known as ion adsorption. Ion adsorption and desorption reactions. In textbook, you guys may known as electrochemical reaction, which is related to the transfer of electrons from electrode to the electrolyte or material within. And this state to store more energy from this electrochemical reaction. Many different electrochemical application has been studied, and we try to use this transient metal sulfide electrode and pseudo capacitor electrodes. And instead of exposure of H2S gas, we deposit this copper mesh and transition metal mesh directly in the sulfide solution. And without any heat treatment due to its high reactivity, it can successfully transport all the bare mesh copper film to the nanostructured Cu2S or CUS films. So we can not well manage the phase of Cu copper sulfide after this direct immersion method, and mostly the copper films are converted to the Cu2S phase. We guess this is due to the lack of the copper sulfide source, a copper source from the dissolved copper mesh. And we figure out this kind of direct immersion or by using a sulfide solution and copper mesh is called the phase hill and low temperature activation process for the copper sulfur activation method. It can be, those kind of nanostructure can be synthesized by the nucleation growth steps. Firstly, the sulfide solution try to dissolve a copper ions from the copper mesh, and they can all the dissolved copper ion try to react with the sulfide solution to convert, and then this reacted copper ions can be converted to Cu2S and try to grow on the copper substrate. And the Cu2S phase has been demonstrated by all the characterization techniques. And by changing the solutions precursors, concentration, and different activation time, we can synthesize a different structure, the Cu2S, and somehow some of the sample shows a single crystalline morphology on the copper on the copper mesh for after this direct immersion. And these days we try to make it as high as possible, as much as possible, to improve its energy performance in terms of CV graph, GCD graph, and EIS and stability, even the full cell energy storage devices. So right now, the capacitance of those sulfide materials reached to the 0.75 millifaraday, 0.75 Fahrenheit per centimeter square at a current density of 2 milliampere centimeter, 2 milliampere square minus square centimeter. And it shows a really high cycling stability up to 90.5% at 20,000 cycles. And also the IABV curve shows that with the B value close to the B value close to the 1, the major energy storage mechanism from energy storage mechanism of this electrode is by ion adsorption, desorption, surface reaction mechanisms. So we keep working on this copper sulfide method, copper sulfide electrode from direct immersion sulfur method. Finally, this copper sulfide electrode also can be working on the flexible situations. Even 180 bending, it can well maintain its capacitance. And due to its highly simple activation method, we can apply this method in roll-through process for the large production, and all the structure materials can be will synthesize even in a different location with a similar CV graph. Then what would be the next target with this simple synthetic method? So by using this highly active sulfur solution, we are now working on applying this sulfide solution and H2S gas on the heterostructure of the other transmetal sulfide with the copper sulfide electrode to design the new electronic device to maximize its electron charge transfer from electrode to the semiconductor materials. And also, these days we are controlling different synthetic structures to make more favorable electrochemical energy storage kinetics for pseudocapacitors, and also due to its high stretchable and flexible properties of copper sulfide and the other transmetal sulfides, we are planning to apply those materials in the stretchable electrode for future energy storage applications. So lastly, those sulfides has been well known for new material catalysts in HER, OER. So designing a new structure, designing a nanostructured 2D and 3D structure material for the catalyst material is my top these days target for optimizing and maximizing the advantage of the sulfur activation method. So this is the conclusion of my my today's research topic. So design of highly transparent and conductive transmetal sulfide electrode, and then design of nano architectures with transmetal sulfide for pseudocapacitors. So thank you so much for your attention. And if you have any question for this designing and finding a new sulfide method, finding and designing new sulfide method with a highly active sulfide solution, please ask me a question. Thank you.
Okay, thank you. Do you have any question? Okay, so due to time the limit, I'd like to go to the next presentation. So let's thanks speaker again. Thank you, Professor. Okay, so next speaker is the Professor Lujun-Ma. And Professor Lujun-Ma, can you hear me?
Yeah. Hi. Hello.
Yeah. Okay. So his presentation title is the application of flexible stretchable electronics and solid state cooling based on functional polymer. Could you start your presentation?
Okay.
Sorry, the Professor Ma, we can hear your voice. Hear our voice?
Hello. Can you hear me?
Okay, we can hear.
Yeah. Okay.
So let's just start your presentation.
Okay. So. Okay. So I started again. So good afternoon, everyone. I'm Ru Junma from Nankai University, located in Tianjin of China. Thanks a lot for Professor Kang's invitation. It's my honor to have this talk here. I'm sorry that I cannot attend this conference physically due to the pandemic. Today, my topic is applications of flexible or stretchable electronics and solid-state cooling based on functional polymers. The most important thing for electronic devices is to have good electrical properties at suitable working temperature. So I will present our work of the electrical performance and thermal management of electronic devices. First, connective flexible adhesives. As a development of flexible or stretchable electronics, conductors, semiconductors, and dielectric layers should possess electrical and mechanical properties at the same time. However, commercial silver paste can be used on the rigid substrate only. When it is bent on the PET substrate, the crack can be observed. In addition, the conductivity of this silver paste is just 10 to 3 GS per centimeter. Conductive silver nanoparticle ink can be used on the flexible substrate, but the conductivity is still low and the curing temperature is high. Here, we fabricated conductive flexible adhesives composed of silver flakes, carbon nanotubes, and NBR to replace commercial silver paste. Nanoscale silver nanoparticles were attached to the side walls of multi-word carbon nanotubes, which constructed effective electrical networks between the micro scale silver flakes to significantly reduce the contact resistance between them and the multi-word carbon nanotubes. The conductivity can be maintained and the bending radius of 5 mm. The resistance change was smaller than 3.5%. When the sample was bent to a radius of 5 mm, the highest conductivity of more than 37,000 JS per centimeter can be reached. Even after 3,000 times bending cycles, there was no any observed crack. The conductive flexible adhesives has very good adhesion. When the silver concentration was reduced to 0.0861, none of the materials were removed from the CFA pattern, even after cross-hatching of the sample. And the helical structure of the CFA pattern, even after and the helical structure of CFA can be stretched and maintain conductivity after 3,000 times stretching cycles. There was only a slight increase in the normalized electrical resistance when the helical rebound was stretched to 600%, which was the maximum strain allowed in the current experimental setup. As a conductive interconnects, the current and the brightness of LED will not change. The current voltage characteristics for the flat, band, and release states were almost identical, demonstrating the excellent performance of the CFA pattern. That is the flexible electronics. Next is the connective stretchable fibers. In our ordinary life, our clothes are knitted using rigid fibers. They can be stretched, even the fiber cannot be stretched. For that reason, we fabricated highly conductive stretchable fibers using wet spinning. The video shows fibers are spinning from needle. The diameter and length of fibers can be controlled. The maximum initial conductivity of the fibers synthesized by wet spinning was more than 17,000 JS per centimeter with a rupture tensile strength of 50%. The maximum strength could be reached to 419%. by decreasing the connectivity to more than 200 JS per centimeter. However, the connectivity of the fiber was decreased when the fiber was stretched. The elasticity of the fiber was bad. To solve this problem, we coated elastic PDMS around fiber, and we achieved excellent mechanical elasticity and electrical reversibility by coating the fiber and fabric using PDMS. The cyclability was also excellent. The electrical performance of PDMS coated fiber was demonstrated using LED chips. To improve the intrinsic elasticity of fiber, we fabricated the fiber using silver flour and polyurethane. The diameter and length of fiber can also be controlled. An extraordinarily high connectivity of more than 40,000 CS per centimeter was obtained by silver nanoflowers, which is 2 orders of magnitude greater than that of fibers synthesized using silver nanoparticles. This was due to the enhanced surface area and the coalescence of nano disc-shaped petals during curing process. After the pre-stretching cycle, the fiber exhibited excellent elastic behavior. During the first stretching cycle up to 70% strain, there was no hysteresis in connectivity during the stretching and releasing process. The pre-stretched fiber demonstrated excellent mechanical elasticity up to 75% strain, and the length of the fiber returned to the initial value after releasing the tensile stress. We can twist the fiber into a rope and use it as elastic interconnect wires. The excellent elastic property of the ropes enable selective illumination of design spot. The LED could be returned to the original position after the illumination. We can also knit the fibers into fabric. The pore was first deformed, and the fibers started to rupture at 210% strain. The connectivity of fabric was not changed and 100% strain due to the structure of fabric. We replaced a long rigid wire using our fabric, and it can transfer signal of force and position. Next is the stretchable semiconductors. Here, I just show our part of stretchable semiconductors. We synthesized titanium dioxide tubes by anodic oxidation. The film of tubes was very brittle, as you can see the video. The stretchability was less than 2%. When we embedded the tube film into conductive film, it can be stretched up to 200% strain, and semiconducting properties were maintained because net structure was formed. We didn't finish it yet. I will move to the solid state cooling part. Here is the solid state cooling. As you know, with the development of electronic technology, the integration of electronic chips is getting higher and higher, and the heat dissipation of chip is becoming more and more prominent. According to statistics, 55% of the chips filler is caused by overheating, and the current cooling of the CPU is through aluminum heatsink, blowing with a fan. The fan does have a good cooling effect, and it can be very small, but when the air temperature is too high, the fan doesn't work. We need to use the air condition. And the current traditional air conditioning is to cool the whole room, large size, pollution of the environment, low efficiency. So the alternative cooling techniques are needed. In recent years, solid state cooling is a good alternative. They show some good performance. However, none of them provides a solution for complex size cooling devices with high power density and efficiency. As you can see here, for the thermoelectric cooling, it is very simple. There's no moving part, but it's low efficiency. The COP is less than 4. For the elastocaloric refrigeration, it is the environmentally friendly, but it needs to extra actuator. It's difficult to scale down. And for the magnetocaloric refrigeration, it has good cooling effect, but it's very heavy, and the space consumption is very large. So here, the electrocaloric cooling can meet the above requirement at the same time. First, they are dielectric materials, pollution-free, almost no power consumption, high efficiency, compact size. When the electric field is applied or removed, reversible temperature and entropy change is realized. So when the temperature of film is increased, the film is attached with heatsink to flow heat. And when the temperature of film is decreased, the film is contact with heat source to absorb heat. Here, many researchers have tried to fabricate cooling devices using different methods. Here, we fabricated cooling devices using PVDF, TFE, CFE polymers, and an electrostatic actuation to rapidly transport a flexible EC polymer state between a heatsink and heat source. The reversible temperature can be observed by applying or removing voltage, as you can see here in the video. Here is when we remove the voltage on the film, the temperature of this film can be decreased rapidly. Okay, so the electrostatic force not only moves the EC film, but also promotes the formation of intimate thermal contact between the EC polymer stack and the heatsink and heat source during each cycle. We control the voltage switching for electrostatic actuation by an electric relay to switch between the silver nanowire anodes of the heat source and heatsink. Here is the video. As you can see, the film movement is between heatsink and heat source. We measure the heat flux on both heatsink and heat source. We also found insignificant Joule heating from the EC effect, verifying that the measured effects are not transient. We found that the heat flux of the PVDF TFE CFE cooling device after continuous operation for more than 1 hour was the same as initial heat flux. We increased the average heat flux of the cooling device by operating at a higher frequency. Also, the electrostatic actuation of the EC polymer stack can operate at higher frequency. The frequency of the PVDF TFE CFE cooling device that gives maximum heat flux is 0.8 Hz, due in part to the time needed to transfer the heat from the EC material to the laminate sheets at the heat source and heat sink. Another way to maximize heat flux is by increasing the electric field of the EC polymer stack. At a frequency of 0.8 Hz, the maximum electric field was set at 66 megavoltage per meter to avoid electrical instability of PVDF TFE CFE cooling device. The EC polymer stack did not show any sign of electrical failure or other damage after 30,000 cycles of charging and discharging. Comparing other solid-state devices, we achieved a heat flux of 30 milliwatt per square centimeter with an applied electrical field across the EC film of 66 megavoltage per meter. And this corresponds to a specific cooling power of 2.8 watt per gram. We demonstrated the benefits of the inherent synthesis and flexibility of our cooling device by fabricating a version that can conform to a non-flat surface, a smartphone battery, and high workloads. In a smartphone, the battery heats up to 52.5 degrees C when allowed to cool in air. The surface temperature of battery measured with a surface mount thermocouple decreased by 3 degrees C in 50 seconds. After the flexible EC cooling device was attached to the battery, the surface temperature of the battery was observed to decrease by 8 degrees C in the first 5 seconds with EC cooling activity. Professor Qiming Zhang wrote the perspectives for our papers. The refrigerant is also the pump. Actually, the polymer film is the refrigerant. Here, in the future, the important things we can make the wearable, maybe we can make the wearable cooling bandage that replace the ice band treatment, and also we can make the cooling of biologic tissues and organs, or we can put the cooling devices on the office desk or put in the chair. The important thing is we can cool the chip. So here is our recent work. We selected the DUP modified PVDF TFE CFE as an active EC material to prepare the EC polymer stacks. DUP with a benzyl ring and a long chain structure acts an interchain lubricant in PVDF TFE CFE to reduce the steric hindrance during the movement of molecular chains and improves the crystallinity. From the cross-section SEM image, a clear boundary between two EC polymer layers is observed, and the thickness of each layer is the same 35 micrometer. When the applied electric field increases from 60 megavoltage per meter to 130 megavoltage per meter, the temperature change of all DOP, modified PVDF, TFE, CFE increase. Then we fabricated a double unit solid state refrigeration device using electrostatic force to achieve the rapid motion of two modified EC polymer stack to pump heat. The double unit EC cooling device can operate in different frequencies. The temperature difference of double unit refrigeration devices is always larger than that of the single unit one and different applied electric field. The COP increases first and then decreases with the increase of applied electric field, and the maximum COP is 0.83 and the electric field of 41 megavoltage per meter. It indicates that there is a great enhancement of electric energy consumption when the applied electric field is larger than 41 megavoltage per meter. Also, large electric field also increases the heat flux of the device. The temperature span of double unit refrigeration device operating at a frequency of 1 Hz is 4.1 K, and the electric field of 60 megavoltage per meter, while the temperature span of single unit device is only 2.8 K. Here, we demonstrated the cooling performance of the double unit refrigeration device for CPU in practice. Overheating can slow down processing power of a CPU, shorten a service life, and even create a fire hazard. The double unit refrigeration device can operate at any time, combined with an automatic control circuit. When the temperature of cooling object reaches the setting value, the EC device startup temperature is 55 degrees C, considering that higher temperature will reduce the efficiency of CPU or even film. From the moment power on the CPU, the surface temperature of CPU without the original cooling system rapidly rises from 29.7 degrees C to 82.6 degrees C in 80 seconds. In contrast, the final surface temperature of the CPU cooled by the double unit refrigeration device is stabilized at 62.2 degrees C. That is the summary. Thank you very much for your attention.
Okay, thank you for your interesting talk. So, do you have any questions? Okay, so I have one question for your cooling system. So,
okay, yeah.
Why do you choose the PVDF among various kind of the piezo pyro materials?
Okay, yeah. As you can see here, actually for the solid state cooling, there are several types of solid state cooling. First one is the thermoelectric cooling. Thermoelectric cooling is very simple. and there's no any moving part, but it has the low efficiency for the thermoelectric cooling. And for the elastocaloric refrigeration, this one is the environmentally friendly, but it needs to extra actuator. And for the magnetocaloric refrigeration, it has a good cooling effect, but it's very heavy and it needs the large space. And for here we use the caloric cooling. Why we select the polymer? Actually, there's two types. One is the ceramic. Ceramic also has a very good performance, but the ceramic is very brittle. It cannot be bent and it cannot be flexible. So, and for PVDF TFE, it has very large delta T. It can reach 12 degrees C, and it has the maximum heat removal of 18.4 joule per gram. So we selected the PVDF TFE and CFE for the cooling film.
Okay, thank you. So anyone have any question? Okay, thank you, Professor Ma.
Okay, thank you.
Unfortunately, we are still missing last speaker. So I'd like to wrap up this session. So I'd like to thank all speaker and participants. Thank you, bye. 하나, 둘,